sharing screen. Let's see. And then this over here, I will do, where's my presentation? This up here. Let's put this up here. Hold on, and then let's see. How do I? Okay, hold on. I'm getting confused. Okay. Okay, seems to have worked. Okay. Yeah, sorry, I messed up something. I even accidentally pinned one of your videos. I actually don't know if that will show or not later on. Okay, now sorry, where was I? I'm gonna open up the chat. Okay, great. Okay, I finally found the chat. Okay, we can start. So so this is week 2. Last week we went through like discrete and continuous random variables, PDF, PMF, joint distributions, law of total probability, conditional probability. We talk about Bayes rule, independence and conditional independence, and we talk about expectation and conditional expectation. Okay, any questions before I continue? Okay. So one key goal in machine learning is signal detection or estimation. Basically, given observation X, we want to estimate Y, right? So basically, we have observation X, and we want to compute Y as a function of X, right? So this is very important because in the real world, we might have to take different action depending on what we think Y is. So in the real world, right, depending on what we think Y is, right? So X might be the cancer test result, and Y is whether the patient has cancer, right? X is the radar signal, and Y is whether there is an incoming missile. X might be a Facebook photo, and Y is the name of the person in the photo. So obviously, detection does not need to be probabilistic. But the world is uncertain, and measuring instruments might have noise and unexpected things might happen, right? So we will focus on basically probabilistic signal detection or estimation. Okay. So what we want to talk about now is about MAP and maximum likelihood estimation. Okay. So first, I want to explain what is argmax and argmin. Okay, so argmax of f of x, right, is the value of x where f of x is the biggest. Okay, so argmin f of x, right, with a subscript x, right, is the value of x where f of x is the smallest. Okay, now for example, f of x is equal to this function, right? Basically, sine 4x squared plus x absolute value e to the power minus x plus x squared plus 0.1. So it's just this funky formula I wrote here for x between minus 0.95 and 0.95, right? Otherwise, it's 0. Okay. So one thing that you will see is that it's generally easier to evaluate f of x than to find the maximum minimum, right? So for example, if I say, oh, what is the value of f of x when x is equal to 0, right? Then in that case, you can simply plug in x into here. Okay. But if I want to ask you, oh, what is the maximum value? What is the value of x where f is the maximum? Then it's a bit harder, right? You don't really know. Okay. So we can plot f of x, which looks something like this. The maximum actually of the function occurs near here, where x is equal to 0.95. Okay, right? And the minimum occurs at x less than 0.95, where is equal to 0, and for x greater than 0.95, right? So there are also local maximum or minimum, right? In many problems, we might only be able to find this local minimum or local maximum, right? So the hills, the top of the hills are called local maximum. The bottom of the hill, these are called local minimum. Okay. Does anyone have any questions so far? Okay, let's continue. So suppose we observe X and we want to estimate Y, then in MAP or MAP estimation, right? Our estimate of Y is the value of Y that maximizes the posterior probability of Y given X, right? So this is what the argmax rotation means, right? So for a particular value of X, right, we can think of this P of Y given X as a function of Y. So we want to find the value of Y that maximizes this function of Y, okay, right? So, and the value of Y that maximizes this posterior distribution is called the MAP of Y, okay? We can use Bayes' rule to rewrite the posterior. So P of Y given X, we can write this as P of Y, which is the prior, times the likelihood, P of X given Y divided by P of X, okay? So the MAP value of Y is the value of Y. Sorry. So first of all, so here P of X, right, does not affect the maximum value of Y, right? So we can just ignore it, right? And so we can drop it, and so we end up with this, right? So the MAP estimate of Y is the value of Y that maximizes the prior P of Y times P of X given Y. Okay. So for example, let's say we have a photo, X is a photo, Y is a chair, right? So the probability of Y is equal to chair given X equal to photo is 0.6. Probability that Y is equal to human given X equal to photo equal to 0.3. Probability Y is equal to cat given X equal to photo is 0.1, right? So the MAP estimate is a chair. So here I've written down such that 0.6 plus 0.3 plus 0.1, right? They add up to 1, okay? And so the MAP estimate is the chair because this posterior probability is the highest, okay? Instead of writing that it's equal, we can also do proportional, right? So the proportion, instead of we say equal 0.6, we can say it's proportional to 1.2, proportional to 0.6, proportional to 0.2, okay? So in this case, if you add up all the numbers, 1.2 plus 0.6 plus 0.2, they're equal to 2, right? So this is not a valid probability distribution, right? Which is why we use proportional rather than equal, right? But the MAP estimate is still the same, which is the chair. Okay, so you might ask, oh, this does not add up to 1. So what is actually the probability event, right? So if you want a proper distribution, what we can do is we can take 1.2 plus 0.6 plus 0.2. This is equal to 2, right? And then we can normalize it, right? We take 1.2, we divide by C. This is equal to 0.6. And 0.6 divided by C, right, is 0.3. 0.2 divided by C is 0.1, right? And so we can see that actually these two distributions are equivalent. It's just that here, when we use the proportional sign, they don't sum up to 1. Okay. Does anyone have any questions about this so far? Okay, it's fine. Okay. Now, let's consider a special case, right? So where all values of Y are equally likely a priori, right? So P of Y is a constant, and so we can drop P of Y, right? So now in this scenario, the MAP estimate is the same as finding the value of Y that maximizes the likelihood of the observation X given Y. So this is called the maximum likelihood estimate, right? So in this case, P of Y is a constant, right? So we can just drop this. Oh, Nitin is asking, how can the probability be greater than 1? So in this case, the probability is not really greater than 1. That's why we use the proportional sign. Yeah. So, and the reason is that actually when we go from this step to this step, we drop P of X, right? So when we drop this P of X, this one, it no longer sums to 1, right? So here, this term here, even though the maximum here is the same as the maximum here, but if you compute here, the sum over Y is no longer equal to 1. This can be greater than 1. Does that answer your question, Nitin? Yes, yeah. So this is the maximum likelihood estimate, right? So in general, maximum likelihood is often easier to compute. And we typically use it when the prior is unknown, or we do not want to assume the priors. So if the number of samples goes to infinity, where there's infinite amount of data, then as you take the limit as n goes to infinity, right, the MAP estimate of Y becomes the maximum likelihood estimate of Y. Okay. Any questions so far? Now, maximum likelihood is a special case of MAP, right? So we can focus on MAP first, right? So in the previous example of the chair, human, and cat, right? I just tell you the number, right? What's the probability that Y given X go to photo, right? But the question is, how do we get this probability in the first place, right? So a lot of machine learning is about how to choose the model for computing P of Y given X, and then how to evaluate and optimize the model parameters. Okay. Any questions so far? So far, it's fine. Okay. Okay. So then, as I was saying, that the focus is on how to model P of Y given X. There are actually two ways of modeling P of Y given X, right? So which are called generative versus discriminative models. Okay, so there are two ways of doing it. So to get the posterior distribution P of Y given X, right, we can apply the Bayes rule, right? So P of Y given X, as I was saying, can be written as this, right? So P of Y is a prior, P of X given Y is the likelihood, and P of X is the evidence term. Okay, so this is the formula from last week as well. And then as I was saying, we don't really need to care about P of X for now. So we can write it's proportional to P of X given Y times P of Y. Right. Again, this is the proportional sign because this, if you sum this over Y, is no longer equal to 1, right? Because we drop off the new denominator. Okay. Now, in generative supervised learning, right, we model the likelihood P of X given Y, and we model the prior P of Y, right? So once we have P of X given Y and with the prior P of Y, then we can apply this formula, right? And then we can then get P of Y given X, correct? Okay. The reason why this is called generative is because we can sample or to generate new data, X and Y, based on this distribution P of X and Y, right? Because P of X given Y times P of Y, right? This is this. So this is the same of P of X and Y. Okay, right? So basically by modeling P of X given Y and by modeling P of Y, we're actually modeling the joint distribution of X and Y, which means that we can in principle sample from this distribution. Okay. So examples are naive Bayes, which we'll cover in a future lesson, next lesson, I think. That's and hidden Markov models. Okay. So now in discriminative supervised learning, right, we model P of Y given X directly, right? Now, because we have P of Y given X, right, we actually do not model P of X. And so we do not actually model the joint distribution P of X and Y, right? And so because of that, we cannot sample the new data X and Y. Okay. Is that clear so far? So examples of these are logistic regression, which we'll also cover in a future lesson, conditional random views, and so on. Okay. Any questions so far? Okay. Oh, Nitin is asking, why do we drop P of X? We drop P of X because let's say if you want to do the MAP estimation, like in the previous slide, right? Then we want to find a Y that maximizes this posterior distribution, right? And so in that case, we can simply drop P of X because P of X is not a function of Y. Does that answer your question, Nitin? So we will be using argmax. Yes, in general, let's say let's say given the posterior, we want to find the most likely class. Yeah. Now, suppose our only goal is to predict Y from X, right? So then, actually the discriminative approach actually most of the time works the best, right? Because you're spending all your computational resources on modeling P of Y given X, right? And so by focusing on P of Y given X directly, a lot of time you can generally get good accuracy. Okay. Now, however, a lot of time generative model might be more interpretable than discriminative model. So for example, suppose you have two features, right? X1 and X2. We're trying to predict Y, okay? X1 is equal to Y plus epsilon, and X2 is equal to minus epsilon, okay, right? So you can think of epsilon as noise, okay? Now, actually a perfect classification approach would be to predict Y to be equal to X1 plus X2, right? So if we predict Y to be X1 plus X2, why is it perfect? Because the epsilon will cancel out the minus epsilon. And so when we predict Y equal X1 plus X2, we get a perfect prediction of Y, right? However, right, if we think about our prediction, right, we're predicting 1 times X1 plus 1 times X2, right? And so essentially, we can think of this as we're weighting the two features equally, right? X1 and X2 both have coefficients of 1, right? So if you interpret the weights of this model, right, 1 and 1, you would think that X1 and X2 are equally important, right? But if you look at X1 and X2, X2 actually does not reflect Y at all, right? The reason why X2 is used in this prediction is because the noise in X2 perfectly cancel the noise in X1, right? So X2 has basically no relationship with Y, right? And so, yeah, and so as a result, generally, the generative model is considered more interpretable than discriminative model. Okay. The generative model also allows us to sample data from P of X and Y. If the data looks realistic, then the prediction accuracy can be high. Okay. So now, even though I motivated generative and discriminative models from the probabilistic perspective, they actually do not need to be probabilistic. Right. So for example, I mean, more generally, right, we can define discriminative models as models focused on prediction. So for example, support vector machines. Okay. What do I mean by sample from X and Y? Let me finish this slide first, right? And more generative definition is that generative models are models that can be used to generate observed data, right? So for example, Newton's 3 law of motion is a generative model because the laws allow us to generate the trajectory of the balls given the external forces and the initial states of the balls. Okay, right? Right. So yeah, let me go back to Samuel's question, right? What do we mean by sample from P of X and Y? When I say sample from P of X and Y, so for example, if you know that there's a Gaussian distribution, P of X, let's say comes from a Gaussian distribution, right? We can sample from the Gaussian distribution, correct? So if we sample from the Gaussian distribution, like if we keep sampling from the Gaussian distribution, we have this distribution that looks like the Gaussian, right? Correct. We plot the histogram of the samples, it looks like Gaussian. So it's the same thing. So similarly, if we're P of X and Y, we can, in principle, sample from it. It may not be easy. In fact, a lot of time it can be very hard, right? but we can in principle sample from it. Does that answer your question, Samuel? So when I say sample, this is what I mean. Yeah. Right. So I talk about generative models in the context of supervised learning, right? But when we talk about unsupervised learning, there's not really such a thing as discriminative models, right? So it's mostly just generative model, right? Where we only have features X, right? So example includes Gaussian mixture models, latent digital allocation, restricted Boltzmann machine, and so on, right? So by definition, right, discriminative models are focused on prediction, right? So discriminative model only makes sense in the context of supervised learning, okay? And then for neural networks can be generative, it can be discriminative, either way, okay? Does that mean a discriminative model predicts the final position of the ball without generating the trajectory? Yeah, so for example, if we're interested in predicting the positions of these balls, right? Then I guess we might not need a generative model, right? Correct. Then we might collect training data of all these balls and moving around, and we just want to predict where the balls will be next. Yes, correct. Oh, sorry. Okay, any other questions? Oh, sorry. I realized that I misunderstood your question, Yinchuan. You're saying that predicts the final position of the ball without generating the trajectories. Let me think. Because you can set up a discriminative model whereby your goal is to just predict every point in the trajectories, right? Correct. Yeah. So it is not. Right. Let me think. I'm blanking out for now. Let me think about this and get back to you. Okay, Yinchuan. Yeah. Yeah. Okay. So so the next thing we want to talk about is that basically once we have selected a generative model or discriminative model, we want to estimate the model parameters, right? Now, so sorry, 1 second. Let me check. So okay, so let's take our previous example, right? Probability of a chair given a photo is 0.6. Probability of a human given a photo is 0.3. Probability of a cat given a photo is 0.1. Okay. So first thing I want to clarify is that if you look at this equation, it doesn't quite make sense, right? Because 0.6, 0.3, 0.1 appears on the right-hand side, but not on the left-hand side, okay? It's similar to what we discussed last week when we say that in the coin toss, you know, remember when we talk about conditional independence and we talk about head, tail, right? Well, we're saying that the probability of head should appears on the left-hand side, right? So it's the same here. We should technically include theta, this parameter's theta, 0.6, 0.3, 0.1, as a variable on the left-hand side, okay? So for example, probability of a chair, y equal to chair, given x is a photo, comma theta is equal to theta 1, right? So theta 1 is equal to 0.6, okay? Probability that y is equal to a human, given x equal to photo, and theta is equal to theta 2, which is 0.3, right? And then probability y equal cat given x equal photo and theta equal theta 3, which is 0.1, okay? So the whole point of this example is to illustrate to you that in this case, this posterior distribution is a categorical distribution with parameter theta, right? And in fact, if we're talking about classification, right, because we're predicting discrete label, we're not predicting a continuous variable, right? Therefore, the posterior distribution is always a categorical distribution. There's no other distribution, right? So in general, theta is not given to us, right? We need to learn theta from the training set, right? Whether it's a generative model or a discriminative model, okay? Theta is the parameters of the model, right? So in this case, theta is the parameter of this posterior distribution, right? Because theta 1 is 0.6, the probability of a chair given the photo. Theta 2 is 0.3, theta 3 is 0.1. Does that answer your question, Arunava? Can I repeat this slide again? Sure. Okay, let's from the beginning. Okay, so far this is so good, right? This is from the previous example, right? So I'm trying to make this a bit more mathematically rigorous, right? By introducing the concept of theta on the left-hand side, right? So instead of writing this, I want to be more explicit because every distribution has some parameters, correct? So in the case of the categorical distribution, theta is the parameters, right? And so, so in this case, theta is equal to, right. So in this case, I have explicitly now conditioned on theta, right? And then in this case, condition that X is for a particular photo and theta, we will grab theta 1, and this is the first element of this theta vector, and it's 0.6. So how does that answer the question? So same with theta 2 and theta 3. Right. And so in this case, as I was saying, for all classification problem, the posterior distribution has to be a categorical distribution, right? With some parameter theta. And this data has to be learned from the training set for both the generative model and discriminative model. Okay. Right. So the Samuel was asking, how do we learn data from the data set? We will talk about this later. Yes. So we will talk about, we'll talk about this later. Okay. Why we include probabilities as parameters? Is that what you're saying? Huakai. You mean probability, right? Not possibility, right? Correct? Yeah, because even if you recall, in the previous lecture, right, when we talk about coin toss, right, the coin toss in the Bernoulli distribution, Q is the probability of getting a hit for the coin toss, right? And so Q is the parameter of the probability distribution, right? So every distribution, every probability distribution has some parameters, right? In some distributions, such as the Bernoulli distribution or the categorical distribution, the parameters itself is some probability. Does that make sense? Okay. Now in the Gaussian, for example, the parameters of Gaussian is mean and variance, correct? Right? And so yeah, is the mean and the variance, yeah, which are not probability, but in this case, theta is a probability. Does this mean not all probability is a parameter? I'm not sure what you mean. So the parameters of some probability distributions are themselves also probability. Does that make sense? So some probability distribution like Bernoulli, right? Or categorical distribution, right? Okay, good. Okay, that answers your question. Yeah, okay. So now in the first bullet point, right? Here, Y and X are concrete thing, right? Photo, chair, human, cat, right? But the whole concept of maximum likelihood and MAP can be used to estimate abstract quantities like theta, right? So basically, we want to treat the parameters of probability distribution as random variables and estimate them using maximum likelihood and MAP, right? So just now I was saying that in the Bernoulli distribution and the categorical distribution, the parameters themselves are probability, right? Now, in the case of the Gaussian distribution, the mean and the variance, these are not probability by themselves, but we can imagine that they are random variables, right? The mean can be a random variable, the variance can be a random variable, right? And so then we can also use ML, maximum likelihood, and MAP to estimate these parameters, right? So basically, right? I mean, this sounds a bit abstract, but I will show you examples after this. In fact, the remaining 2/3 of this lecture will be about this: how to treat parameters of probability distributions and random variables and estimate them using maximum likelihood and MAP. Okay. Okay. Now, I'm going to elaborate a bit more, right? So imagine that we're focusing on a classification problem, right? And so we have a training set D. The D has features xi, y, and the target label yi, right? And the n sample. So I goes from 1 to n, capital N. Okay. Aruna is asking, so we'll calculate MAP of probability of data given. Yeah. So actually in this slide, I'll talk about this. Yes, how we're going to do this, right? So now, so the idea is that suppose we have a generative model. We came up with a generative model, right? P of X and Y given theta, right? Now we can estimate the parameters of this generative model from the data D, right? And then once we have this data, once we have this parameters data, right? And then given a new test sample X, right? We can predict Y of the new test data using the MAP estimate of the posterior, right? Basically, given the new test data X, right? We want to predict Y, right? And so we can write down the posterior distribution of the new Y given the new test data X and our learned parameter theta, correct? Now, we can then do this as a proportional. We can write this proportional as P of X and Y given theta. And we can in turns break this down into P of Y given theta and P of X given Y theta. Okay. Is everyone okay with this part? Or you need me to just do it in more details? Okay, so P of Y, sometimes it might be easy to just write. I like writing, right? So P of Y given X and theta is equal to, is equal to P of X and Y given theta and P of X given theta. Is that right? Yes, that's right. Okay, and remember that this does not contain Y, right? So we can just drop it off and we say it's proportional to P of X and Y given theta. Okay, so this is the proportional part. What I just shown you here is a proportional part. And then from here to here, this is just saying P of X and Y given theta is the same as you first observe Y given theta. And then after you observe Y and theta, you observe X. Okay, so that's why this equality is true. Okay, is that okay, Samuel? Okay, now, so there are two strategies here. As I said that we want to estimate theta, right? So we can treat theta like a random variable, right? So we can estimate theta using the maximum likelihood strategy, right? So basically we want to find the model parameters theta that maximizes the likelihood, the P of the data, the training data set D, given the model parameters data, right? So this is, if you recall, this is the definition of maximum likelihood, right? Correct? So this is the maximum likelihood strategy for estimating the maximum likelihood estimate of theta, right? After we have the maximum likelihood of theta, given the new test data X, right? We want to predict the new test label Y, right? So then we can plug theta, the maximum likelihood of theta, into this, right? P of X and Y given the maximum likelihood of theta, right? Which, if you recall, is proportional to the posterior distribution of Y given X and theta, right? And so this will allow us to find the MAP estimate of Y. Okay. So this might be slightly confusing, right? Step one is actually using the maximum likelihood strategy, but step two is again the MAP strategy, right? So step one, we're using the maximum likelihood strategy to estimate theta. Step two, we're using the MAP strategy to estimate Y. Okay, so the step one and step two are, the goal are different, right? So this is like training. Step one is like training. Step two is like testing. Okay. Another strategy is to use the MAP approach to estimate the MAP to estimate data, right? So if you compare these two, if you compare the two step one, you see they're different in the sense that this is P of D given theta. This is the likelihood. This likelihood of theta. P of theta given D. This is the posterior distribution of theta given D, right? So this is why this is called maximum a posteriori, right? Because we want to find the theta that maximizes P of theta given D. Okay. Now let me think. After that, right? So in step 1, we use the MAP strategy to estimate theta. Given that we've estimated theta, right? We can then plug in into the joint distribution of x and y given theta, right? But here we're using the maximum likelihood estimate of theta. Here we're using the MAP estimate of theta, right? And then we find the MAP estimate of y. Okay. Which estimate of y is better? In theory, actually strategy 3 is better, but we will talk about that in the future. Yeah. Okay. Yes. Any questions so far? Any other questions so far? So basically from here, right? Basically we have a model, right? We have a, let's say we have a generative model P of x and y given theta, right? In the training set, we want to estimate theta, right? And in strategy 1, we estimate theta using maximum likelihood estimation. In strategy 2, we estimate theta using MAP estimation, right? And in either way, after you have the estimate of theta, you can plug it into the joint distribution to find the MAP estimate of y. Both of these strategies are generative because we will be able to find. Oh, hold on. Sorry, there are 3 questions I missed. Let's start with the first question. Why strategy 1 also finds MAP estimate of y? Because these 2 steps are doing 2 different things. So this step is trying to estimate theta. This step is trying to estimate y. Correct? So here, so there are 2 things we want to estimate, right? The model parameters, that's in the training set, we want to estimate the model parameters. In the test set, we just want to predict y, right? So actually So actually we can use different strategies for step 1 and step 2. There's nothing stopping us from doing that. Does that answer your question, Yun Yi? Yeah. Strategy 1 and 2 are both, sorry, hold on. Let me go to Aruna first. For the first one, for maximum theta, we have to find D first, right? Oh, for the first one, oh, sorry. Sorry, 1 second. For the first one, D is given to us. D is a training set D, so we don't need to find D. We are given D, that's a training set D, and we want to find theta. Does that answer your question, Arunava? And in both of these strategies, they're generative because we will be able to obtain P of x and y given theta, correct? So I like to separate the modeling from the estimation process, right? So our model is P of x and y given theta. So this model is generative because once we have learned theta, right, we can, in principle, sample from this distribution, right? So it's generative, right? How you estimate theta, it doesn't matter, right? You can just do a very bad job in estimating theta and you would still have a generative model, right? So the strategy here is how to estimate theta. Does that answer your question, Yanjun? Yeah, so it's same, we have the same question. So whether we're doing strategy 1 or 2, our model is a generative model, right? These are just 2 different ways of estimating the parameters of our generative model. So Y is for predicting or testing. Hold on, sorry. I missed some questions. Sorry. Nitin is asking. Arunava is asking, it is written of argmax theta D given theta. Right. So, sorry. So this one is just the, So this one is just the definition of maximum likelihood. There's no concept of whether like this is a generative model or not. This is just a probability distribution. When we talk about, does that answer your question, Arunava? In strategy 1, shouldn't it be argmax P of theta given D? No, it's not. If you look at the whole point of why strategy 1 is because we're doing a maximum likelihood, right? Remember, if you remember, when we go back to what is MAP, right? So in MAP, right? You remember y is something we want to predict, right? So this is the posterior distribution, right? X is the observation, right? So this is called MAP, right? Whereas here, this is called maximum likelihood because y, we still want to estimate y, but x is our observation, right? Correct? So in general, if we have p of some parameter we want to estimate given theta, and we're doing argmax of the parameter, right? Then this is MAP, right? If we do P of data given the parameter, right? Then this is called maximum likelihood. Does that answer your question? Yeah. So MAP and ML is you need to sort the thing. Yeah. Samuel, sorry. Hold on. Sorry, let me go back there first. Okay, sorry. Let's see. So Y is for predict. Facia is asking. Oh no, Samuel is asking. But is it proportional to the discriminative model? I don't understand what you're asking, Samuel. Which part is the proportional to the discriminative model? Oh, sorry. You elaborate further on. But P of Y given X and theta is discriminative modeling. No. P of Y given X and theta is not necessarily discriminative modeling, right? If you look here, one second here, we are always interested in P of Y given X, right? Even though we're interested in P of Y given X, right? You can model P of Y given X in a generative way where you model P of X and Y, or you can model P of Y given X in a discriminative way where you model P of Y given X directly. Yeah. So in both generative and discriminative model, in the end, you want to compute P of Y given X. Yeah. Okay. Good. I love questions. Keep going. Okay, let me go back here again. So then I'm a few minutes behind the questioning. So Y is for predicting or testing. Sorry, which Y? You mean this Y here, is it? So Y is already in the test set. So we are given a new test sample X and we want to predict the label Y of the new test sample X. Does that answer your question? Fei Xue. Okay. When to use strategy 1 or 2? We will go about that later on. So in general, I would say strategy 3 is the best, but we haven't covered that yet. Strategy 2 is if you have a lot of data, strategy 1 and strategy 2 doesn't matter, right? There's no difference. Well, if you have a lot of data, then all 3 strategies does not matter, right? But if you have less data, then maybe strategy 3 is better than strategy 2, which is better than strategy 1. Okay. I think I'll answer Liu Chen's question as well as Rong De's question. Would it, Linker is asking, would it be right to say that maximum likelihood is what kind of parameters will maximize an algo fit to the data, and MEP is what kind of algorithm will best fit to the data? I mean, those are just words, right? So it's hard for me to say whether they are correct or wrong. So it's really just go back to this, okay? What are you optimizing? Right? So if the parameter is what you want to estimate, right? If you're optimizing P of parameter given theta, then this is MAP. If you're optimizing P of data given parameter, then this is maximum likelihood. Okay. Yeah. So let's see example. Well, I hope the next thing is an example. Yeah. Yes. So as I said, this all seems a bit vague. So let's go into step one. We'll now talk about a few distribution, the beta binomial distribution, and then we can talk about step one for maximum likelihood and step one for MAP, and actually maybe a bit of strategy 3 as well. Okay, we won't go into step 2 until next week, where we talk about something else. Okay. Okay, so basically, the parameters of probability distribution are treated as random variables, right? So we're going to see how this can be done for various distribution. Okay, so now, let's see. How are we doing on time? I think we're doing fine. So let's take like a 4 minutes break until 6:50. That's an early break, I think. But I think it's a good place to take a break. Okay, all right. Yeah. We'll come back at 6:50. Yeah. Okay. Okay, it's 6:50. I'll appreciate if y'all can yeah, can turn on your videos again. Okay. Let's see. Shall we share screen? How's my pace today? Am I going too fast or is it okay? A bit fast or I hope it's not too fast. Okay. Yes. Okay, let's share screen. Okay, let me try to see if I can slow down. Okay. Yeah. Okay. So the next part is the, oh wait, hold on. Did I successfully share screen? Or today I seem to have a lot of Zoom issues. I keep screwing up. Yeah. Oh, where's the Newton is asking, can I say MAP is always better than ML since ML is a special case of MAP? No, I guess in MAP you need to assume a prior, and if your prior is good, then you can get better results, actually. But sometimes if your prior is bad, you might get worse results. Yeah. But when you have limited data, then some form of prior could be helpful. Hope that answers your question. Yeah. Okay. Yes. Today's I would say in terms of difficulty level, this week and next week will be the hardest part of my half. Yeah. Then after that, the difficulty level will go down for week 4 and 5 and 6. Yeah. Okay. So the first thing I want to talk about, the next thing I want to talk about is this beta binomial generative model. So here we don't really have a y yet. We're still not predicting something yet. So it's just x, really. Okay. So suppose we have n coin tosses, right? So of these coin tosses, we get n0 tails and n1 heads. Okay, in n coin tosses. So the data consists of n0 tails and n1 head. Okay. Theta is the probability of getting a hit. Okay. Then this is a coin toss, right? So and then we toss it n times. So we actually have a binomial distribution, right? So the binomial distribution is written as n choose n1 theta to the power of n1 times 1 minus theta to the power of n0. Okay, that's the binomial likelihood. Okay. So far so good. Okay, so theta is the parameter of the binomial distribution, right? So we're going to assume a prior on theta, right? So theta is a probability, but itself it can come from another distribution, right? So in this case, what people sometimes do is that they assume a beta prior on theta, right? So P of theta, it has two parameters A and B is equal to the beta distribution with parameters A and B, right? So A and B are scalars, they're greater than 0, and they're called hyperparameters, right? And the formula is given by this, theta to the power of A minus 1 times 1 minus theta to the power of B minus 1. There is a 1 over B of A and B, right? So this is a normalization constant. So that, so here, this is the distribution over N1, correct? If we sum over all different values of N1, it has sums to 1. So can someone tell me here, what would you sum or integrate to get 1? Correct. So you would integrate over theta, right? Because theta is, why integrate? Because theta is a continuous variable, right? And then so 1 over b of a and b is a normalization constant to ensure that when you integrate this integral is equal to theta, is equal to 1. And in fact, actually, b of a and b is given by this formula. Yeah, this is a gamma function. Yeah. Anyway, okay. So now what is important to note here is that if you compare these two distributions, they look very similar, right? Theta to the power of something, 1 minus theta to the power of something. Theta to the power of something, 1 minus theta to the power of something, right? So this is not an accident. And this is why people use the beta prior, because it makes the math convenient. Okay. Now, here's the distribution of the beta. Sorry, this is a visualization of the beta distribution, right? So when a and b are equal to 1, so it's a red line here, then we get a uniform distribution, right? If a and b are less than 1, then we get the blue line here, where basically you're more likely to get extreme values of theta. So theta is more likely to be 0 or more likely to be 1, close to 0, close to 1. If a and b are both greater than 1, so for example, the black line, right? Then you get a distribution which is closer to the center. You get a peak in the middle, okay? Right? Now, if a is greater than b, right? If a is greater than b, then the distribution will be skewed towards 1. If a is less than b, the black distribution, then it'll be skewed to the left. Okay, right? What else do I want to say? If a and b becomes bigger and bigger, then the distribution becomes narrower and narrower, right? So you can see that if you compare AB, 8 is equal to 2 and b equal to 3, a equal 8 and b equal 4, you can see that the green distribution is narrower than the black distribution, right? Okay. How the probability is more than 1. Again, theta is a continuous variable, right? So this is not the probability, this is the PDF. Does that answer your question, Arunava? Yuan Train is asking, is this like doing a coin toss experiments, but I don't know the theta value of the coin? Yes, yes. You don't know the theta value of the coin, but the theta is generated from some distribution, right? Right. So if my factory, yeah, okay, yeah. So if my factory is good, maybe I'll generate my beta distribution will be something like this. My fair coin factory, right? Then I'll generate coins that is all very close to 0.5. Okay, right? But my factory might not be so good. And also I'm not supposed to make coins. I guess I'm not the treasury, so I cannot make coins. Okay. Yeah, okay. Okay. So so then the question is that suppose you observe the n coin tosses and you want to estimate theta, correct? Right? So then let's compute the posterior distribution of theta given that we have observed some coin tosses D, right? So the first step is to write it in this form. This is the base rule, right? This is the prior of theta. This, which is in this, this is the likelihood function, and then this is the evidence. Okay. The likelihood is given by the binomial likelihood, right? So I just copy here. P of theta, this is given by the beta prior, so I just copy here. Okay, so far so good. Okay, so now I'm going to rearrange some terms, right? I'm going to start by, okay, so n choose n1, I'm going to copy here. That's a 1 over BAB, right? I'm going to copy here. Okay, now I'm going to collect all the thetas term together, right? You see, you have theta to the power of n1 and theta to the power of a minus 1, right? So if you group it together, it becomes theta to the power of n1 plus a minus 1. Let's see. And then you can group the 1 minus theta together. You have 1 minus theta to the power of n0, 1 minus theta to the power of b minus 1, right? And so we get 1 minus theta to the power of n0 plus b minus 1. Okay. Now, there's p of d, and then I just copy here. Okay. So far, so good. Right. Now, at this point, if you look at this distribution, right? I hope you see, sorry, hold on. I hope you see that this distribution almost look like it's not in the form theta to the power of something 1 minus theta to the power of something, right? And so it's actually looking a bit like the beta distribution. And so now our goal is to try to manipulate this so that this becomes a beta distribution. Okay, so we're going to introduce, this is basically equal to 1, right? B of n1 plus a, n0 plus b divided by b of n1 plus a, n0 plus b. Okay. If we do that, what we're going to do is we're going to group it the following. If you look at the blue portion, which I have already circled up, right? This is exactly a beta distribution. Okay. This is a beta distribution with parameter n1 plus a, n1 plus a, and parameter n0 plus b, n0 plus b. Okay. There's also all this red stuff, right? Which I am simply going to call kappa. So kappa is a function of n0, is a function of n1, is a function of a, and is a function of b, right? So I'm just going to put kappa here. Okay, and p of d, I just put it here. Okay, so far so good. Any problems so far? Okay, so now the magical thing that appears is that it turns out that kappa and p will essentially, the ratio is actually equal to 1. And so we end up with this. This is beta theta of n1 plus a, n0 plus b. Okay, and the reason why this ratio will be equal to 1 is I can show it to you. Let me see. Let me do this. What's the easy way to do this? Okay, let me first show you. The left-hand side is P of theta given D, correct? Let me just copy it here. P of theta given D, right? And then the bottom is this kappa term. This is kappa. Oh, I need to leave some space. This is equal to kappa n0, n1, comma AB. This is a beta distribution, beta of theta, given n1 plus a, n0 plus b, divided by p of d. Is everyone okay with this? I'm just copying, all I've done is to copy this equation here, and then to copy like the left-hand side p of theta given d, I copy here. Okay, everyone is good? Any questions? Okay, now I want to show you that this kappa divided by p is 1, right? So the trick here is to integrate the left side with respect to theta, and we integrate the right side with respect to theta, right? So if we integrate the left side with respect to theta, can someone tell me what is the left-hand side? One, correct. Left-hand side is 1. Because this is a distribution over theta, if we integrate respect to theta, we'll get 1, right? What will happen to the right-hand side, right? So this term actually does not contain theta. This term does not contain theta, right? Correct? So effectively, we're integrating beta with respect to theta, right? Because the beta distribution is a distribution over theta, if we integrate over theta, so integral of this beta distribution is also 1. Okay. And so we end up with kappa n0, n1, a comma b, p of d, right? So this is why the ratio is equal to 1, right? So very conveniently, this kappa divided by p is equal to 1, and so we end up with just this beta distribution. Is everyone okay with this? Any questions? Okay, so, so this posterior is obtained by essentially we add the hyperparameters, the prior hyperparameters a and b to the observed count, right? Because this is n1 and n0 are the actual count. n1 is the number of hit, n0 is the number of tail, right? So we're adding a and b to the counts, right? And so a and b are called pseudo count, right? Okay, it's as if we observe some head and tails before we even observe head or tails. Okay, So the posterior distribution, this is the posterior distribution of theta. It has the same form as the prior. The prior is a beta distribution. The posterior is also a beta distribution, correct? So we say that the beta distribution is a conjugate prior of the binomial distribution. Okay. So this is just a definition, is a vocabulary that you should learn. Yeah. Okay. Any questions so far? Okay, so this is just an example, right? So showing basically, let's say your beta distribution is a red line, right? The binomial likelihood looks like the black line, and the posterior distribution is the blue line. Notice that the blue line is between the black and the red, right? Same here. The blue line is a posterior, is between the black, the likelihood, and the red prior. So in general, the posterior is trading off between our prior belief and the observed data. Okay, right? Any questions? Okay, so now let's say you have the posterior distribution, right? We can perform the MAP estimate of theta, correct? Or the maximum likelihood estimate of theta, right? Correct? So let's do that, right? So for a beta distribution, the mode is given by C minus, sorry, so this is a beta distribution with parameters C and D, right? And the mode is given by C minus 1 divided by C plus D minus 2. So the mode of the distribution is the peak of the distribution, okay? So this formula comes from Wikipedia, right? But in fact, we can derive it using just calculus. We can differentiate ourselves and so on. And so we can do this in this week's assignment, this week non-graded assignment. Okay. Now, in the previous slide, I've shown you that the posterior distribution of theta is given by the beta distribution with parameters n1 plus a and n0 plus b. Okay. So the MAP estimate of theta, right, is basically we want to find the value of theta that maximizes the posterior distribution P of theta given D, right? But the posterior distribution is the beta distribution, right? So we can just plug in C to be N1 plus A and D to be N0 plus B, okay? And so we end up with this. Okay. So if you recall, okay, so this is the MAP estimate of theta. For the maximum likelihood estimate of theta, remember the maximum likelihood occurs when the prior is flat, right? So in this case, if you remember, the beta distribution is a uniform distribution if A is equal to B is equal to 1, right? So if we set A equal 1 and B equal 1, we end up with N1 divided by N. So it makes a lot of sense, right? So this is the maximum likelihood estimate is the proportion of hit that you observe. The maximum likelihood of estimate of theta is the proportion of hit we actually observe. Okay. Does anyone have any questions? Oh, why A equal B equal 1? Oh, because it's just that we know. One second. So for the beta distribution, remember that when A equal B equal 1, then it's a uniform distribution. Yeah. And so maximum likelihood equal MAP when we have a uniform distribution, right? Okay. Ken, sounds good. Okay, so now I want to kind of show you that MAP estimate is in some sense a trade-off between the maximum likelihood estimate and our prior. Oh, the mode. Liu Chen is asking, what does the mode mean? The mode of the distribution is the peak of the distribution. So the mode of this red distribution is here, right here. The mode of this black distribution is, if you draw a straight line down, is here. It's not the maximum value of distribution, is the value of the x-axis where it's the maximum. Does that make sense? Yeah. Yes. So it's like argmax. Yeah, it's like argmax of the distribution. Yes. Okay. So I'm gonna take this formula here. This is the MAP estimate. This is the maximum likelihood estimate. I'm gonna copy it here, right? Okay. And then I'm going to define M0 to be A minus 1 divided by A plus B minus 2, right? This is actually the mode of the beta distribution, the prior beta distribution, right? And then alpha 0 is equal to A plus B minus 2, and it's like the pseudo count, okay? As we say, the MAP estimate is this is just copied from here, right? I will skip some steps. This is just algebra. You can go home and check it out. But essentially, we can write the MAP estimate to be 1 minus lambda times the maximum likelihood estimate plus lambda times the prior mode. So remember, the prior mode is defined here. Okay, right? So again, you can see that the MAP estimate is basically a weighted average between the maximum likelihood estimate and the mode of our prior distribution. What is the meaning of the posteriors in between the prior and the likelihood? Right. So for example, in this picture, notice that the blue curve, which is the posterior, is between the black and the red curve. So that's what I meant. Yeah. And in this case, I'm making it more mathematically explicit. That was just some picture I showed you, right? So here I'm showing you exactly, right? The MAP estimate is the weighted average of the maximum likelihood estimate and the prior estimate, right? Right. So if our prior is weak, so when alpha 0 is small, right? When alpha 0 is small, this term is small, right? So lambda is small. So lambda is equal to alpha 0 divided by n plus alpha 0, right? So if our prior is weak, right, this lambda is small, and so MAP estimate is closer to the maximum likelihood estimate, right? If we have a lot of data, if n goes to infinity, when n goes to infinity, right, if you look at lambda, this is lambda. As n goes to infinity, this term becomes 0. All right, yeah, this term becomes 0, right? And so again, the MAP estimate goes to the maximum likelihood estimate. Okay. When there's very little data n and alpha is very big, right? Then obviously, then we're weighted more towards the prior. Okay. Any questions? Why do we set A equal B equal 1? Oh, okay. So you're talking about here, is that right? Zhao Qi? Right. So here we're trying to derive the maximum likelihood estimate, right? If you recall, let me see if I can find the slide. In the maximum likelihood estimate here. So remember that if we have the MAP estimate, right? And we assume that the prior P of Y is a uniform distribution, then we get a maximum likelihood estimate. Do you remember this part, Zhao Qi? Right? So once we have an MAP estimate, if you want to get an ML estimate, you can just set P of Y to be the uniform distribution, right? Right? So now, in the case of the beta distribution, the beta distribution is uniform if we set A and B to be equal to 1. Okay. Yes. Okay. Why we use P of theta given D to replace P of theta? Actually, which part are you talking about? Zerling. Sorry, oh, you mean like here? Are you referring to like here? Are you referring to which slide are you not clear about? Why we use P of theta given D to replace P of theta? So P of theta is the prior distribution, right? This is the prior distribution of theta, right? Oh, sorry, is my current page correct? Or you want to go to the last page I was discussing? So let's say I give you a coin, right? I give you a coin and you have not tossed any coin yet, right? then this prior distribution of theta is saying what is your belief about theta, about the theta of the coin, right? Before you even toss it, correct? And then, so this is the prior distribution, right? But then after that, we observe some coin tosses, N1 head and N0 tail, right? And so after we observe some head and tails, we can now compute what is the posterior probability of the theta given all the coin tosses we have observed, right? And the whole point of this is saying that after we observe we have made some observation, right? Our posterior, which is, let's say, this blue curve, is essentially we're waiting between our prior and our likelihood. The likelihood is our data that we actually observe. The prior is our belief before we observe anything. Does that help, Zerling? Why P of theta equal? Oh, right. So Jikai. So here, hold on. Where are you reading this from? This P of theta is not the posterior, right? Oh, I see. So here, okay, maybe you're talking about here, right? P of theta, I plug in this, right? Correct? Right? So think of this as P of theta is, when we write P of theta and A and B, right? We're actually just being very explicit about what is the parameters of the distribution, correct? So a lot of time we might be lazy and we write this. Oh, we might be lazy and we write this, right? Because we don't want to overload, we don't have too many symbols in our equation, right? But every distribution has some parameters, right? So for example, a Gaussian distribution has the mean and the variance, right? So similarly, the beta distribution has the pseudo count A and B, correct? And so when we go from here to here, we're just making it more explicit that our beta distribution depends on A and B, right? So for example, let's say X is a Gaussian distribution with mean 0 and 1, right? Correct? We can write P of X, right? Or we can write P of X given the mu is equal to 0 and the variance is equal to 1. Does that make sense? Jikai. They're the same thing. It's just that here I'm kind of like being lazy, right? I don't explicitly write the mu and the sigma. Does that answer your question, Jikai? Yes, Jikan. What does convex oh wait, hold on. No, in some sense it's a conditional probability, right? We're saying that what is the PDF of X given that mu is equal to 0 and sigma square equal 1, right? So in some sense, it is a conditional probability. Yeah. Sometimes it's just that sometimes the conditions are not we are always conditioning on something. It's just that sometimes we're not being explicit what we're conditioning on, right? Okay, so Fei Shui is asking, I still wonder why P can be above, right? As I was saying in the first lecture, right? In this class, P of X is equal to PDF if X is continuous, and P of Y is equal to PMF. Oh, sorry, P of X equal PMF if X is discrete. Do you remember this thing? I think I mentioned that a few times last week, right? Fei Shui, right? So then, if X is continuous, the PDF can be greater than 1, correct? In general, you remember that PDF can be greater than 1, right, Fei Shui? And so, right? So for PDF, the PDF must be greater than 0, and the integral has to be equal to 1, right? But the actual PDF can be greater than 1. Does that make sense, Fei Shui? Samuel is asking, how do you differentiate? You mean You mean, oh, how do you differentiate between the two? Oh, right. How do we differentiate whether we're talking about this or this? This is a good question. It comes with experience. I don't have a good, I'm sorry, I don't have a good solution for you. Yeah, I don't have a good solution for you. Yeah. Yes. It can be confusing sometimes, even for me. Yes, even for me. It can be confusing sometimes. Yeah. So here, do A and B has any practical meaning like mean and variance? Yes, actually, as I was saying here, if you look at here, right, the posterior distribution is parameterized by n1 plus a, n0 plus b, right? So you can think of A and B as pseudo counts, right? Basically, you can think of A, as the coin tosses, the number of coin tosses before you even observe, sorry, the number of hits before you even observe the hit, any coin tosses, right? And B is the number of tails before you observe any coin tosses. Does that make sense, Ling Guo? So that's why we call it pseudo counts. Yeah. Okay. And then for a more mathematical kind of feeling of what they are, I will ask you to refer to this graph. So usually when I get a strange function, I like to plot it, right? So given this function, right, if I were you, you should try to plot it to see what it looks like, right? So I'm just plotting it for you for different values of A and B to give you intuition of like, oh, as A increase, what will happen? As B increase, what will happen? If A and B both increase, what will happen? Does it make sense? So here, this plot is showing the different possibilities. Okay. Okay, so where was I? Okay, now we want to predict future coin toss, right? Remember last week we were talking about 99 coin toss and about the 100th coin toss, right? So now let's do this in a more formal way, right? Actually, last week, due to your questions, I already did a little bit of that, right? So suppose we are given training data D, N0 tails, and N1 hit, and X tilde is the next coin toss, right? What is the probability that X tilde is equal to 1? Here, one is equal to hit, right? So what's the probability next coin toss will be a hit? Okay. So strategy 1, right? There are many ways to do this, right? So let's say we just assume that the probability that the next coin toss is hit is just the maximum likelihood estimate of theta, right? Strategy 2, we can say that the probability the next coin toss is hit is the MAP estimate of theta. Okay, right? But actually, none of these are really quite correct, mathematically speaking, right? So because if you look at the questions above, you look at here, right? The first 2 bullet point, right? The question is saying, suppose we're given N0 tails and N1 hit. What is the probability the next coin toss is 1, right? So actually what we want to evaluate is P of X tilde is equal to 1 given the training set, right? And it's not, I mean, as you will see in the next slide, this is not the same as maximum likelihood or MAP. Okay, right? So does anyone have any questions? Well, the next slide we'll try to evaluate this. Okay. Now, from Wikipedia, right, for beta distribution with parameters C and D, the mean of the beta distribution is given by C divided by C plus D. Okay. Now, the posterior distribution, I previously showing that the posterior distribution of theta has parameters N1 plus A and N0 plus B, right? And we're interested in X tilde, the outcome of the future coin toss. Okay. We want to know what's the probability that the future coin toss is 1, given that we have observed some coin tosses, correct? The first step to do is to apply the law of total probability, right? We can introduce a theta here. So P of X tilde equal 1 given D. We can do P of X tilde equal 1 and theta given D. And we integrate with respect to theta. Okay, this is called the law of total probability, right? And then we can split this probability up. P of X tilde equal 1 and theta given D is the same as P of theta given D. times P of X tilde equal 1 given theta and D. Okay, so this is just conditional probability. Okay. Now from here, right, given that we already know the true value of theta, right? Given that we know theta, we can just drop D, right? So basically, the future coin toss and all the previous coin tosses are conditionally independent given theta, right? This is why I tried to emphasize last week, right? And so this is equal to P of X tilde equal 1 given theta. And then P of theta given D is just copied here. Okay. Now, why is the probability that X tilde is equal to 1 given theta? That is simply theta, right? Because theta, remember, is the probability of getting a hit, right? Okay. And so if you look at here, this is actually the mean of the posterior distribution, right? So this is the expected value of theta given D, right? And so, oh, which part, Samuel? You mean from which equality? This one? Okay, let's call this wait, this one? This first one? Is it? Okay. So the first one, you have trouble. Okay, that's fine. Okay, let's see. Let me do again. So, okay, so you know that in general, P of A is equal to integral P of A and B dB. Are you okay with that? Oh, yeah, yes, right? So here, and then we can always condition on something and it's always true. So P of A given C is equal to integral P of A and B given C dB, correct? Okay. So here, if you compare, let's say A is X tilde equal to 1, C is equal to D, right? And then B is equal to theta. So this equality. Are you okay with that? Is everyone okay with that, Samuel? Okay, good. So do you need me to explain this equality as well, or no need? Anybody needs me? So for this equality, this is something like we are trying to expand P of A and B given C, right? So remember, P of A and B is equal to P of A given B, P of B, correct? Right? So we're essentially applying this formula, except now we have an additional condition on C, right? Correct? And so we can always write this as P of A and B if we condition on C, P of A and B condition on C, P of B condition on C, right? You can always add more conditioning, right? And so now again, if A is equal to X tilde equal to 1, B is equal to theta, and C is equal to D, then is the same thing. Okay. Then let's see. From here to here, Xijia is also concerned about the conditional independence. So this one is just saying that, remember last week's example where we have 99 coin tosses, then the future coin toss is independent of the 99 coin tosses, given theta, right? Given that we know last week we were using the symbol Q, right? So from here to here, we can just drop D because all the previous coin tosses are independent of the future coin tosses if we already know theta. Does that answer your question, Xijia? Okay, then from here to here, why is this equal to theta, right? This is equal to theta because, you mean this equality. Why is this equal to theta? Because theta is the probability of getting a hit, right? So I'm asking you, what is the probability that X tilde is hit, given that theta is the probability of getting a hit, right? So therefore, the probability of getting a hit is just theta. Does that make sense? Chen Kian? Yeah. Okay. So then this is the mean, the expectation of theta given theta. Sorry, expectation of theta given D, right? And so we use the formula from above. We plug it into the formula. C is N1 plus A, D is N0 plus B, and we get this, right? Okay. So the next part is going to be a hand waving part, right? So this posterior distribution, right? As remember, the posterior distribution is a beta distribution, right? As n goes to infinity, the posterior distribution becomes a delta function at the MAP estimate of beta. So what is the delta function? For those of you who are not from electrical engineering, the direct delta function is actually 0 everywhere, except at a particular location where it has infinite height and the area is equal to 1, right? So essentially, what this sentence is saying is that as we have more and more data, this posterior distribution becomes a very sharp distribution at the MAP estimate, right? And so when you do that, then essentially then P of theta given D can be written as the direct delta function centered at the MAP estimate of theta hat, right? And so if we use the sifting property of the direct delta function, right, this is equal to the MAP estimate of theta. Can draw? Okay, sure. So essentially actually I can, okay, let's see. Let's put it this way. Remember I was telling you that as n becomes bigger, the distribution becomes narrower and taller, correct? Samuel? Yes. So what I'm saying here is that as n goes to infinity, right? Think about what is happening to the pseudo count, right? As n goes to infinity, n1 and n0 are going to become bigger and bigger, right? Correct? And so as n1 and n0 becomes bigger and bigger, this beta distribution becomes narrower and narrower and taller. Okay, right? And what will happen is that as n goes to infinity, this beta distribution, let's say this is 0, 1, this theta, the beta distribution will be at, let's say here, will be very sharp, right, at the MAP estimate. Okay, right? Is everyone okay with this? Okay, so this is as n goes to infinity, right? Then the posterior becomes narrower and taller until it becomes the direct delta function. Okay. I will, why MAP and not ML? I will explain later. As n becomes infinity, they'll become the same. Yeah. Okay, so let me finish this part first, Zishan. I'll answer you right after this. Okay. The mode is theta MAP and is also equal to the maximum likelihood estimate. Yeah, did that answer your questions? Because as n goes to infinity, they become the same. Okay. Oh, I almost didn't let you see. Right. Okay. Right. Why is the mode at theta MAP? The mode is at theta MAP because remember, the MAP estimate is the mode of the posterior distribution. So by definition, the mode of the posterior distribution will be your MAP estimate. Liu Chen. Yeah. Right, because remember, MAP estimate is obtained by maximizing your posterior distribution, right? But the MAP estimate is the mode of posterior distribution. Okay, right? So basically, this is called the plug-in approximation to the posterior predictive density, right? So essentially, this is also equal to the maximum likelihood estimate if n is big, right? And so essentially, remember I was telling you that 1 second, please. I was giving you these 3 strategies, right? So the strategy I just showed you is the posterior predictive strategy. And these 2 strategies are called a plug-in estimate, strategy 1 and 2. Okay. And right. And so this is extremely common. But essentially we are estimating theta. We are estimating the model parameters data from the training data set, and then we apply to the test data, right? But as you can see here, you can overfit because we're basically ignoring that there is some uncertainty about our model parameters estimate, right? We're estimating theta, and there's some uncertainty associated with theta. But in the plugin approximation, right, we just say, oh, let's screw it. Let's just use our estimate as if it's true. Okay. Okay. Zixuan is asking, isn't P of A and B given C, isn't it equal to P of A given C, P of B given C? This is actually not true. This is actually only true if A and B are conditionally independent given C, right? In general, P of A and B given C is equal to this. This is always true. This is always true. Now, if A and B are conditionally independent given C, then we can drop B and we end up with this. Hold on. Yeah, then we can drop B and end up with this. So this is always true if A and B are conditionally independent given C. Does that answer your question, Zixuan? Strategy 3, which is called the posterior predictive distribution. So this thing, the title, this is called the posterior predictive distribution. Yeah. And then Samuel, sorry, hold on. So hold on. Newton is asking, why is the mode that theta MAP? Remember MAP is we want to find a parameter that maximizes the posterior distribution, right? Correct? The mode of the distribution would maximizes this, right? Correct? Therefore, the mode of the posterior distribution is the MAP estimate. Does that answer your question, Liu Chen? Right? So when we say mode of the distribution, let's say P of Z equal R max of Z, P of Z, correct? Right? So is the mode of distribution of Z is saying the value of Z then where P of Z is the biggest, right? Correct? And so if P of Z is equal to this, the posterior distribution, then we're saying that the mode of the posterior distribution is the MAP estimate. Okay. And Nitin is clarifying, is this for MAP and ML, they are both called plug-in approximation. Yes, that's correct. Okay. Let's continue. Okay. Now, in the black swan paradox, right, instead of using, oh, sorry, hold on. So this overfitting can be sometimes known as the black swan paradox. Oh, can y'all just take a screenshot if y'all want now? Because the thing is very messy. I'm not sure, is it of value to you that I upload this? Yeah, I actually was not writing this in sequence. Yeah, sorry about that. Do you want to take a screenshot now if you're looking for it? Yeah. Sorry about this. How about, okay, starting from now, I will try to write things in a more organized fashion when I scribble it, because here I was just treating it as scratch paper. So for those now, you can just take a photo, okay? I will start afresh. I'll start a new paper. Okay, and I can, yeah. Okay. But for now, you should take a photo. Yeah. Okay. All right. Now, as I was saying, instead of posterior predictive distribution, we can just use, let's say, the maximum likelihood estimate or the MAP estimate, right? And so in the case of maximum likelihood estimate, then is equal to N1 over N. Okay, right? So the problem is when the sample size is small, the maximum likelihood can be terrible, right? So let's say N is equal to 3, so you toss a coin 3 times. But let's say all 3 times are tail, and so then you'll conclude the maximum likelihood estimate of theta be 0, right? And so you would say that heads are impossible for future coin toss, right? But that really doesn't make sense, right? Because you only observe 3 coin toss. I mean, you could just be unlucky, right? They observe all tails, okay? Now, nowadays you talk about big data and all this stuff, but actually once you start partitioning data based on certain criteria, let's say number of times a certain person is engaged in a certain activity, the sample size becomes very small, right? Right. So in general, once you start focusing on, let's say, trying to predict the habit of a single person, the sample size becomes very small, right? So this is called the black swan paradox, right? In ancient times, the Europeans have only seen white swans, right? Using the maximum likelihood estimate, this would imply black swans can never be observed, but actually black swans were found in Australia in the 17th century. Okay. We can resolve this paradox using the posterior predictive distribution, right? So let's say we assume a uniform prior. So A is equal to B is equal to 1, right? Then the probability of observing the black swan is, using the posterior predictive distribution, n1 plus 1 divided by n1 plus n0 plus 2, right? So even though in Europe, you have never observed a black swan, but this distribution is never 0. Okay, there's a fancy name for this. It's also called Laplace smoothing. Okay. Now, MAP estimate will not solve this, right? Because here, remember, we assume A equal B equal to 1, right? When A is equal to B is equal to 1, the MAP estimate is the same as the maximum likelihood estimate, right? And so in this case, if you're in Europe and you have never observed a black swan before, your MAP and maximum likelihood estimate will both be 0 probability of observing a black swan. Okay. Okay. Does anyone have any questions? Can we choose different values of A and B other than 1? Of course we can, and that's the next example. Okay. Shall we go to the next example? Okay. So I want to give you an example of how this can be used. So let's say, because so far it's a bit abstract, right? So for example, how can we set the hyperparameters of the beta distribution, A and B, right? So imagine that you're a recruiter and you're trying to hire baseball players. Okay, so I stole this example from this website. Okay. So imagine that you have 2 players you're trying to recruit. Player 1 has only tried to hit the ball 10 times. And out of this 10 times, player 1 has hit the ball 4 times. Player 2 is more experienced. Player 2 has tried to hit the ball 1,000 times. And out of this 1,000 times, player 2 has hit the ball 300 times, right? Correct? Now, we know that the typical baseball player hits the ball maybe 26%, 25.9% of the time, right? If we just look at player 1 and 2, player 1 is hitting 4 out of 10, so it's like 40%, right? But it could be luck because he has only tried to hit things 10 times, right? Whereas player 2 has a lower proportion, 3 out of 10, right? But so 30% is worse than 40%, right? But actually he has tried 1,000 times, right? So it feels like he's not, maybe he's really above average, right? So in fact, if we look at some real players in history, right? If we sort players by the batting average, right? So if you look at these 5 players, right? Their batting average is actually 100%, right? They hit their balls 100% of the time. But that's because they have only tried 1 or 2 times and they were lucky and they hit 100% of the time, right? Correct? If the players with the worst average, they have 0 times, right? They hit the ball 0 times, 0% of the time. But again, maybe they were unlucky because they have only tried a few times, 4, 7, 4, 9. Okay, right? So we wouldn't say these are the best players in the world. We wouldn't say these are the worst players in the world. Okay, right? So what can we do? So let's start by visualizing kind of the batting average of all baseball players, right? So this is a histogram of the batting average. Okay, the mean is around 0.27, right? In fact, actually, we can fit a beta distribution to this histogram. Actually, we can perform a maximum likelihood estimation of A and B, right, by fitting to this distribution. If we do that, then we find that A is 78.7 and B is 224.9. And you can see that the beta distribution actually fits this quite well, actually, right? Now, given that we have this beta distribution now we can go back to the problem, right? So remember, we have two baseball players. One hits 44 out of 10. Player two hits 300 out of 1,000, right? And we have a beta distribution. A is 78.7. B is 224.9, right? The prior mean is A divided by A plus B is about 25.9. Okay. Anyway, so we can compute the posterior predictive distribution for player one. This is the formula that I taught you just now, right? 4 plus A divided by 10 plus A plus B, so 0.263. And player two is 300 plus A divided by 1,000 plus A plus B, which is 0.291, right? So even though player two, the batting average is 30%, and player one, the batting average is 40%, but if you look at their posterior predictive distribution, player two is actually higher, and so we should recruit player two. Okay. Does anyone have any questions? Okay, so in that case, we're almost done with this section. Let's just do a quick. Hold on. Let's just do a quick. Yeah, let's try this again. Let's see if this works. Sorry, 1 second. I should have tried loading this earlier. Sometimes it's crazy. Okay, let's see. You can go to. Oh no, it's not loading. Why is this happening? 1 second. Oh, it's thinking very hard. Maybe it is loading. Sorry, 1 second. Let me do this again. Did this work? Oh, wow, it took a long time, but I think maybe it worked. Why is it taking so long? There we go. Okay, let me see. Let me try here. Can y'all see it? Oh, it doesn't work for you. It's not working, huh? Okay, let's try again. Okay, it's working now. Oof, that was tough. The software seems to have degraded. It in previous years when I did this, does not. Yeah, it's not so sluggish. Okay. Okay, so yeah, John, he did 20 hits out of 100 chance. And we assume the beta distribution is 70-200. So what's the posterior probability that John does not hit the next ball? Does not, okay, does not hit the next ball. Oh, yes. Sorry, Anton. Yeah, you go to this website that Yanjun posted. In the interest of time, 1 more minute, and then like 7:50 will stop. Okay, whoever has not answered is okay. Okay, 7:50. I think it stopped. So actually, the correct answer is actually the third one. So the first answer is actually the probability John will hit the next ball, right? So 1 minus this is actually this. I think for those who select this, I think you just make a careless mistake. 1 minus the first option is actually this, is not this. Okay. Chen Rui, you're asking, Niting is asking the same question. How do we arrive at A and B? I don't actually quite understand. The example does not answer your question. The example here does not answer your question. So in the baseball example, how do we get 78.7 and 224.9? Is that right? Is that what you're asking, Nitin? Oh, I see. So you can write so you can perform in the baseball example, right? Baseball example. You can compute probability of the data given A and B, right? Where argmax, right? A and B, right? So this is the maximum likelihood estimation, correct? Because this is the data given the parameters, right? And in this case, the data is the distribution here. Okay, so if you work it out, you will get A and B to be 78.7 and 224.9. Does that answer your question? Yeah. Okay. So it's 7:52. In the interest of time, today is slow. Okay, let's take a 3 minutes break. Okay, all right, let's take a 7:55. We come back. Okay, 7:55. I appreciate if y'all can turn on your video again. I think we're in good shape. The last part is quite short. Okay. Let's see. Where was I? Okay. So the beta binomial distribution was about hold on. Sorry, let me bring up the chat. Where's the chat? Very annoying. Hello. Oh, chat. Okay. All right, the chat is back. Okay. So the beta binomial distribution was about tossing coins, right? Now we're going to talk about rolling a dice. So the categorical distribution, right? So the Dirichlet multinomial distribution, right? So let's say there are n rows of a k-sided dice. So we roll the dice n times, right? And the dice has k sides, okay? And so we will have observed, this is our data set we observe, whereby n subscript k is the number of times k shows up on the dice, right? So let's say n1 will be the number of times the first side of the dice show up, n2 will be the number of times the second side of the dice show up, okay? And theta k is the probability that k shows up on the dice, right? And then how many thetas are there? There are capital K theta, because this is a k-sided dice. So we have theta 1, theta 2 to theta capital K. The collections of all the theta is also called theta. Okay. Now, the probability of observing the data given theta, right? So this is called the multinomial likelihood. It's like the binomial likelihood has two possibilities, right? Head or tail, right? So the multinomial likelihood it has, I guess, more than two possibilities. It has two or more possibilities. Okay, right? So we can write this as n factorial divided by n1 factorial times n2 factorial dot 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 n capital K factorial. Okay, and we can write this as a product from small k equal 1 to capital K, theta k to the power of nk. Okay. Now, I write this in proportion, so we can just ignore all the factorials first. We can write it in this form, right? Okay. In some sense, this is quite similar to the binomial distribution, right? Because if you recall, the binomial distribution is also theta to the power of something. So same, this is also theta to the power of something. Okay. Now, we want to, now in the binomial distribution, right, we assume kind of a beta distribution, right? So now we want to generalize the beta distribution to this case. So this is called the Dirichlet distribution, right? So we're going to assume a Dirichlet prior on theta. And this Dirichlet distribution has k hyperparameters, alpha 1, alpha 2, all the way to alpha capital K. Like before, just like in the beta distribution, all the alphas are greater than 0. Okay. And then here's the formula for the Dirichlet distribution, P of theta given alpha. We write this as the Dirichlet distribution, theta given alpha, right? So basically, remember, all the thetas have to sum to 1, correct? All the thetas have to sum to 1, which means that if the theta doesn't sum to 1, it's 0, okay? It is only non-zero if the thetas are greater than 0, greater than or equal to 0, and all the thetas sum to 1, right? Because remember, theta is a probability that you get the k side of the dice, right? So all the thetas has to be greater than or equal to 0, and if you sum up all the theta, it has to be equal to 1. Okay, and so the distribution is given by this 1 over b of alpha. Again, this is the normalization constant, right? Product small k equal 1 to capital K, theta k alpha k minus 1. Okay. Again, if you compare the two, you see that the formulas are very similar, right? Theta k to the power of something, theta k to the power of something, right? And again, this is not an accident. This is so that the math will work out. Okay. Remember, I told you that is only the Dirichlet distribution is only non-zero when the theta k's are greater than 0 and they sum to 1. So if let's say k is equal to 3, so here's an example where k equal to 3, right? So then here theta 1 is 1, theta 2 is 1, theta 3 is 1, right? If we draw a triangle, right, connecting these 3 points, right? This triangle is only theta is only non-zero. Sorry, the Dirichlet PDF is only non-zero inside this triangle, right? Because within this triangle, theta is greater than or equal to 0, and the sum of theta is equal to 1. Okay, this triangle is called a simplex. Okay, right? It's just a fancy name for a triangle, right? Okay. This is 3 variables. Obviously, you can repeat this in 4 variables, 5 variables, but our human mind can only comprehend up to 3D, right? So I'm only drawing in 3D. Okay, right? Okay. So then here's an example, right? So I take this simplex. Anything outside the simplex is 0, right? So I can take this triangle and I can make it 2D, right? Correct? Right? So this corner is theta 1, this corner is theta 2, this corner is theta 3. Okay. If alpha is equal to 2, 2, 2, if alpha is all 1, then it's a uniform distribution, I think, over the triangle. If alpha is 2, 2, 2, 2, then you start having this peak in the middle of the triangle, right? If alpha is 22, 2, then you can see this distribution is closer towards theta 1, right? This means that without observing any data, right? Because this is a prior distribution, right? So this means that without observing any theta, we are likely to get a dice whereby the probability of getting the first side of the dice is high. Does make sense, right? Whereas here, this is more in the center, so we're more likely to get a dice where it's a fair dice. Okay, where all sides are equally likely. Okay. Any questions about the Dirichlet distribution? Can we say alpha is the weight? Where do you come up with that name? So we usually call alpha the hyperparameters, and alpha, I guess, can also be called like the pseudo count. Why do you want to call it the weights? Yeah, I guess you can call it the weights if you want, but I don't know if that's the common terminology. Yeah. Weight with respect to theta. I see. No, I mean, we typically just call it pseudo count, I think. Yes, for the same reason why in the beta distribution, we call A and B pseudo count. You can call this pseudo counts. Yeah. Okay. Oh, I see. So you can, yeah, so you can see that here, the pseudo count for the first side of the dice is high, right? It's as before you roll the dice, it's as if you have already observed the dice have gotten the first side of the dice 20 times, right? So that's why it's called pseudo count. This is not the beta distribution. This is called the beta function, which is different from the beta distribution. I'm sorry. Yeah, they're all it's a standard notation. They call it B, so I still use the same B, but it's not the beta distribution. Yeah. So like before, this B exists so that when you integrate with respect to theta, you get 1. Okay. Now, let's see. Like before, right? After you observe some dice rolling, you want to compute the posterior distribution of theta given D, right? We start the Bayes rule, right? This is the prior, this is the likelihood, this is the evidence term. Now I'm going to skip some steps because the derivations is very similar to before, right? Essentially, you plug in the multinomial likelihood, you plug in the Dirichlet distribution, right? If you do that, notice that this is theta to the power of something, theta to the power of something, and so you can group it, right? And so you can write this as product from k equal 1 to capital K, theta k, and k is here, alpha k minus 1 is here, alpha k minus 1, right? I read proportional because I'm ignoring like the kappa and all this stuff. Remember from the beta binomial distribution, I skipped it this time. Okay, and so essentially, if you work out the math, and I encourage you to try it at home, right? If you work it out, you will get that this is the Dirichlet distribution. Now with parameters n1 plus alpha 1, n2 plus alpha 2, and k plus alpha k. Okay. Now the posterior is obtained by adding the hyperparameters alpha 1 to alpha k, right? Alpha 1 to alpha k, we're adding it to the actual observed count, right? So the alphas are called the pseudo count, same as before, right? And then how to calculate or get alpha? Alpha is a hyperparameter that you set, right? So one thing I should mention is that in this kind of thing, hyperparameters is like you can get it just now in the baseball example. We did it using it's called an empirical based approach, where we estimate the priors in the data, right? Priors from some historical data. A lot of time you can also set out the hyperparameters using a cross-validation procedure. Let's say you have a training set, validation set, and test set, right? You can try different hyperparameters in the training set and apply it to the validation set. And with the best result, you pick the hyperparameters, the best result in the validation set. And then you use this hyperparameter and you apply it to the test set. Does that make sense, Lo Wei? Yeah. Okay. So like before, this distribution, the posterior distribution is a Dirichlet distribution. The prior distribution is also a Dirichlet distribution, right? So we say that the Dirichlet distribution is conjugate prior of multinomial distribution. Okay. Okay. And you can confirm for yourself if k is equal to 2, then you should get the same result as the beta binomial. Okay, right? Okay. Any questions? Now, this is the MAP ML estimate for the Dirichlet multinomial model. Let's see, do I want to do this? Oh yeah, okay, fine, I'll do this. Okay, so for a Dirichlet distribution, the mode of the Dirichlet distribution xk, remember now x is a vector of length capital K, right? Correct? And remember xk sums to 1, okay? So the mode xk at subscript k, right, is equal to gamma k minus 1 divided by sum over all the gammas minus capital K, okay? Again, I just took this from Wikipedia, but you could work out, you can derive this using calculus, okay? Now, the posterior distribution, as I was telling you, is given by the Dirichlet distribution with parameters n1 plus alpha 1, n2 plus alpha 2, and so on, right? Now, what is the MAP estimate of theta, right? The MAP estimate of theta, remember, is the mode of the posterior distribution, right? So the mode of the posterior distribution, right? We can just use this formula, but now we need to set gamma 1 to be n1 plus alpha 1, gamma 2 to be n2 plus alpha 2, and so on, right? So if we plug it in, we get the MAP estimate for theta k hat is equal to nk plus alpha k minus 1 divided by n plus sum over k alpha k minus capital K. Okay. Is everyone okay with this? Now, to get a maximum likelihood estimate, remember we assume a uniform distribution, right? And the Dirichlet distribution is uniform over the simplex if we set alpha k to be 1, right? So if we set alpha k, all the alpha k to be 1, we get nk over n, right? And so essentially, theta k maximum likelihood is a fraction of time the kth side of the dice shows up out of n dice roll. Okay. Again, you can double check. If capital K is equal to 2, you should get back the similar formula to the beta binomial distribution. Okay. Any questions so far? Any questions? Is MAP same as posterior predictive posterior? No. The MAP is not the same as the posterior predictive. Remember the let's see, yeah. Remember we had 3 strategy, right? The posterior predictive is not the same as MAP, yeah. Yes, yeah. They are only the same if n is very big, if you have a lot of data. Okay, I'm actually not sure where I am. Oh, hold on. Okay, so now actually this section parallels the previous section, right? We first did MAP ML, now we want to do the posterior predictive distribution, right? But to do this, it's worth showing you how to do the mode of the Dirichlet distribution. I think I won't show it to you, but I would encourage you to read it. It's actually quite useful because you know, you get to you get to do things like the Lagrangian, which you don't get to use that much. You have the Lagrangian because all the theta needs to sum to 1. So you need to introduce this Lagrangian when you differentiate, right? And then anyway, if you solve it, then you get you get the mode of the Dirichlet distribution. Okay. Okay. I won't walk through it. Okay. Okay, so now let's do the posterior predictive distribution, right? So let's say we have, this is our data, right? We have n1 to n capital K, right? N1 is the number of times we observe the first side of the dice and so on, right? So X tilde is the outcome of the next dice row, right? What is the probability that X tilde is equal to I, right? So again, same as before, strategy 1, right? We perform a maximum likelihood estimation to find theta, right? So then we say the probability that the next dice row is the ith side of the dice is the ith element of theta ml, right? So theta ml, remember, is a vector of length capital K, right? So theta I ml is the ith element of the vector. Okay. In strategy 2, right, we get an MAP estimate of theta, and then we just use it to predict the next dice row, right? But again, like I told you, right, they are not actually correct, right? Because the question is saying, suppose we have observed some dice row, what is the probability that the next dice row is from the side I of the dice, right? So we want to compute the probability that the next dice row is the ith side of the dice given capital D, where D is all the previous dice rows we have observed, okay? Right? So it's not the same as I'll show you in the next slide, right? So just to let you know, based on Wikipedia, right, for a Dirichlet distribution X with hyperparameters gamma 1 to gamma K, right, the mean of Xi, so Xi is the ith element of X, right? X, remember, is a vector of length K, right? Xi is the ith element of X. The expected value of Xi is equal to gamma I divided by sum of over all the gamma. Okay. Now, the posterior distribution, I've shown you just now, right? The posterior distribution of theta has hyperparameters, is the Dirichlet distribution with hyperparameters n1 plus alpha 1, n2 plus alpha 2, and so on, right? And X tilde is the outcome of the future dice row. Okay. We want to compute the probability that X tilde is equal to I given D, right? So now this is like, actually the derivation is very similar to the beta binomial distribution, right? We first use the law of total probability to introduce theta. So we introduce theta here, right? So we integrate with respect to theta, right? So if we integrate with respect to theta, we get this, okay? So this integral, as I say, is an integration over the simplex, okay? Now, this is the conditional probability that we talk about, right? P of X tilde and theta equal D. Sorry, P of X tilde and theta given D is the same as P of theta given D times P of X tilde given theta and D. Okay. And then this is the conditional independence, right? If we already know theta, remember theta is the probability of getting the different hits. The probability of getting the different sides of the dice, right? If we already have theta, then the previous coin tosses, the previous dice rolls and the future dice rolls, right? The past and the present, the past and the future are conditionally independent, right? So the previous dice rolls and the future dice rolls are conditionally independent, and so we can drop D. Okay. And then the next step is, right? Theta is the probability of getting different sides of the dice, right? So the probability of getting the ith side of the dice is simply theta I. So it's the ith element of the vector theta. Okay. And so this is the expected value of theta I given D. And so we can use this formula from here, right? Except now gamma 1 is n1 plus alpha 1. Gamma k is nk plus alpha k, right? And so if we do that, we get ni plus alpha I divided by n plus sum over k alpha k. Okay. So in the case of a posterior predicted distribution, this is even more important in multinomial, right, than in the binomial case, because the data become more sparse as we partition data into more categories. Okay. Does anyone have any questions? So yes, this is the I guess this is a task process in the sense that we're trying to predict the next dice roll. Yes. Just to give you now I'm going to give you a kind of a toy example of how of using this, right? It's a toy example because nowadays there's much better ways of modeling, you know, this kind of text sequences. Okay, so here we're going to use predict the next word in the text sequence, right? So let's say this is a text sequence. Mary had a little lamb, little lamb, little lamb. Mary had a little lamb, is fleece as white as snow, right? So the first thing we can do is that we can consider kind of a dictionary of words, right? Mary, lamb, little, big, fleece, white, black, snow, rain, unknown. UNK is unknown, right? So unknown is used to capture certain useless word like had and its and so on. Okay. Sorry, it is used to capture right. So, okay, we're going to ignore certain punctuations and stop words like a, as, there, and then we're going to count the frequency that a word appears, right? So, Mary, little, Mary, lamb, little, big, fleece, white, and so on, right? So this is the dictionary words, and count is the number of times the dictionary words appear in the sequence. So in this case, Mary, if you look at this text sequence, Mary appears twice. So this is 2. The word lamb appears 1, 2, 3, 4 times. So lamb is 4, right? So this is called the bag of words representation. Basically, you just count the number of times the word appears, right? It can give pretty good results in natural language processing, but as you all know, nowadays with the large language models, you know, they can perform much better. But yeah, but I'm just giving you an example. Okay. So now let's assume in this case that alpha is equal to 1, right? Then we will have the probability that x tilde is equal to I, right? The probability that the x tilde is equal to I, right? So the probability that the next word we see, x tilde is the next word we see, right? Is equal to the I dictionary word, is equal to this, the formula, the posterior predicted distribution from before, right? Where alpha I, we plug in alpha I equal 1. The sum of all the alpha, that are k dictionary words, right? So this is 10. How many words have we seen? We've seen that 16 words here, right? So this is 16, right? And so if we compute this, so P of x tilde given this sequence is this 3 over, this is the distribution we get, right? So the most likely words are little, 5 over 26, and lamb, 5 over 26, okay? There are some words like big, black, and rain, right? They have a non-zero probability, even though they have never observed in the data. Okay, so this is why the posterior predicted distribution is useful, because it allows you to have non-zero probability, even for words you have never seen. All right, UNK stands for unknown. Thanks for answering, Arunava. Okay, does anyone have any questions? Why do we want non-zero probability? It's the same reason as the black swan paradox. We don't want a zero probability of seeing a black swan, right? So similarly, in a text sequence, we want a non-zero probability that a new word will appear, right? Yes. So in some sense, to avoid overfitting, yes. Will the ML MAP outcome be different based on different model that we use? Yes, of course, it would be different, right? So for example, even using the same model, the Dirichlet multinomial distribution, right? If we have different alpha, then the MAP estimates will be different, right? Correct. So the MAP estimate, so like here, the MAP estimate has alpha. So if we have different hyperparameters, the outcome would already be different, right? if we use different models, obviously the MAP estimate will also be different, right? So here we're using, you know, so here we're using this very simple bag of words model, right? Correct. If we use a more complicated model, like nowadays, these natural language processing, they use this big language model like BERT or whatever, right? Or GPT, right? Then obviously the MEP ML would be different. Yeah. When do we use Dirichlet multinomial versus beta binomial? Yeah, I think Zhang Chen has answered it. Basically, if it's a binary, then we use beta binomial. Categorical, like a rolling a dice, then it's Dirichlet multinomial. Okay. Oh, generative versus discrete. Oh, wait, hold on. I mean, oh, I see. Huali was saying that if we use a generative versus discriminative model. Right. Yes. Of course. So the strategy, the modeling strategy will be very different, of course. Yeah, generative versus discriminative. Yes. The ML MAP results will be different, of course. Yeah. So in week 4, hold on. In week 4, I'll teach you logistic regression. So that's a discriminative model, and obviously, the MAP results will be different. Yeah. Sorry, the output will be different. Yes. Yeah. Does that answer your question, Wally? Wiley. So in this slide, we're basically using the, okay, sorry, just to be clear, right? In this slide, so far, there's no Y, right? So just now when we talk about generative versus discriminative, right? We have X and Y, right? We're trying to use X to predict Y, right? So here, in some sense, we have all X, right? We're using X to predict X. So here, in some sense, there's not really a super, there is not really we're using the current to predict the future, right? So it's not quite as clean as X and Y. Yeah. Why sum of AK equal 10? Oh yeah, no, this is just a hyperparameter. So we decide to set alpha to be 1, right? For example, this example. For example, if we set alpha to be 1, then if we set alpha I to be 1, then alpha I will be 1. And then because all the alphas are 1 and capital K is 10, right? Because we have 10 dictionary word. So we add alpha 1, alpha 2 to alpha 10, then we get 10. Does that answer your question, Sitya? Okay. Which one is useful, generative or discriminative? So in general, right, if you're trying to just predict stuff, I think a discriminative model would be better. Okay, right? If you want some interpretation, then actually I think a generative model might be easier to interpret. Okay. Lingo is asking, if we want to predict next word, should this be conditional probability problem, which is mainly based on the last word in a sentence? Yeah. So here, the reason why this is not that good a model is that it is using a bed of words, so it ignores the sequence of the words, right? Correct. Nowadays, in the big language models such as GPT-3 or whatever, right? They have a model whereby they actually try to encode all the past history, right? And so they would take into account the fact that the next word is actually coming after snow, S, Y, S. So it's trying to take that into account. Yeah. But in this example, we're saying screw it. The ordering of words doesn't matter. So we just use this bag of words representation. Does that answer your question, Lingpo? Okay, let's do one last, or let's see if this will work. Yeah. Okay, just now it didn't work very well. Oh, yes, it's working for me. It's working for me. Oh, someone's very fast. I guess in the interest of time, once it hits 8:28, we'll stop, even if people have an answer. Okay, yeah, it's 8:28. So actually the answer is yes, because as I was saying before, the beta distribution is like a special case of the Dirichlet distribution, right? So you can imagine that you have you have a two-sided dice. A two-sided dice is basically like a coin, right? Correct. So the Dirichlet distribution is a special case of the. Sorry, the beta distribution is a special case of the Dirichlet distribution. So Danny is asking, what is the meaning that it can for a generative model? What's the meaning that it can generate? Observe data or new data. Basically, it's actually like what the name says, right? Because we have, as I said before, if we have a Gaussian distribution, right? P of x, let's say x is from a Gaussian distribution with mean 0 and variance 5, right? So then because we know P of x, right? So we know P of x, right? So we can sample from P of x, right? Correct. So given that we know because we know the distribution of x, so we can sample from P of x. So in some sense, we can say that we know the generative model of x, right? So in the case where we're talking about, right, we're talking about a discriminative, we're talking about a supervised learning problem, right? So we have x, we have feature x, we want to predict y, right? So then if we have P of x and y, right, we know P of x and y, so we can sample from P of x and y, right? And so we say that if we model P of x and y, then this is called a generative model, because once we estimate the model, we can sample from the joint distribution. Does that answer your question, Danny? Yeah. So Wiley is asking, in the slide, MAP and ML estimates of data are deduced from which model? Right. So in this case, in the beta binomial and the Dirichlet multinomial distribution, in some sense, today is a generative model. Yes, these are generative model. Yeah, it's a generative model, right? But in some sense, it's a generative model because it only has x, right? It doesn't have y, right? Because in this case, x is the coin tosses, right? They only have the coin tosses. Yeah. In which occasion do we use Dirichlet model to predict the probability? I guess if you have I'm actually not quite sure, Xijia, why asking. Basically, oh, I see. Right. So in this case, the Dirichlet multinomial distribution is for the case where you basically have a dice roll, right? Correct. So in cases where you can write down categorical variables, like in this example, right? Then we could use the Dirichlet multinomial distribution, right? Because the Dirichlet distribution is the conjugate distribution of the categorical or the multinomial distribution, right? And so anytime you have a categorical distribution, you could use the Dirichlet distribution. So generative model could handle situation of only one variable, discriminative not. Yes, in some sense, yes, because because in discriminative model, you usually have a target variable you're trying to predict. Yeah. Right. Samuel is asking why in the future x tilde is not the same as y. This is a good question. It is not the same because it is actually because it's actually from the same distribution. So if it's from the same distribution, we usually don't distinguish that, right? So imagine if you toss a coin, if you toss the coin, x is the coin toss, right? You don't really differentiate between the future x and the current x in the sense that the past x in the sense that one is the y, one is the x, because in each case the future coin tosses might be dynamically changing, right? Usually, okay, let's put it this way, right? Because if we observe 50 coin tosses, right? The future coin toss might be the 51 coin tosses, right? If we observe 100 coin toss, the future coin toss might be the coin toss number 101, correct? So in this sense, the y is always changing, right? The y we want to predict is always changing, right? Whereas typically when we talk about in the supervised learning case, right, we have x and we want to predict y. In these cases, it's a bit more static, right? So x is like the MRI images, y is the subject, right? That we are. What y is whether the patient has Alzheimer's disease or they're healthy. Does it make sense, Samuel? So typically for the supervised learning, we have we typically have the y is a bit more fixed, right? In the coin tosses, yes, the future coin tosses, you can think of it as we're trying to predict the future coin toss. So that can be our y. But in this case, depending on the problem setup, the target you want to predict is constantly changing, right? Does that kind of make sense, Riley? So in this case, I don't really consider this as, yeah, I differentiate. I wouldn't consider this as supervised learning. Yeah. So for generative model, we don't need to estimate theta, but can estimate y directly. Again, yes, we can estimate x directly. Yeah, we can in this case we can predict x directly without estimating theta, right? In this case, for example, we have the it's not that we don't estimate theta, but we compute the posterior distribution of theta, right? But we don't say theta is equal to 0.3, theta is equal to 0.5, right? So what we're doing here in the posterior predicted distribution is that we are keeping the full distribution of the full posterior distribution of theta. Okay, does that answer your question, Tani? Okay, let me wrap up, and then we can stay on for more questions, right? So today we talk about probabilistic signal detection estimation, right? Which is kind of a key goal in statistical machine learning. I've talked about MAP estimation and maximum likelihood estimation, right? MAP estimation corresponds to finding the mode of the posterior distribution, and maximum likelihood is the special case of MAP estimation where the prior is uniformly distributed. And let's say if we want to model posterior distribution, and there's two approaches for that: generative and discriminative models. The parameters of the probabilistic models can themselves be treated as random variables, and then we can estimate them using MAP or ML. We talk about the concept of conjugate prior. Today we talk about the beta binomial generative model, where the binomial parameters are beta distributed. We have a Dirichlet multinomial generative model where the multinomial parameters are Dirichlet distributed. And we talk about how we can use these models, generative models, to predict future coin toss or dice roll. Okay, right? And the proper way to do that is using the posterior predictive distribution. If we use a plug-in approximation, so using the MAP estimate or the maximum likelihood estimate, if we have a lot of data, then that's fine. If we don't have enough data, this can result in overfitting, known as the black swan events. Okay. So these are just some optional readings you can do, and that's all for today. Okay. Does anyone have more questions?
Hi, Prof. Sorry, can I just ask just to clarify the difference between generative?
Right, Yan Xuan, I cannot hear you.
Oh.
Oh wait, hold on, no, is my microphone is too soft. Okay, go on. Go on.
Oh,
yeah.
Yeah. So I just want to clarify the difference between generative and discriminative models, right?
Mm-hmm.
So the whole idea behind generative is that we can generate new data. So
yes.
Vectors are all generative because given our beta distribution, we are able to generate more
yes.
samples.
Yes.
Okay.
So we can start off by sampling a theta, let's say from the beta distribution. Then given the theta from the beta distribution, we can sample the coin tosses, right? Correct.
So the point is to be able to predict a set of hyperparameters such that we can generate new data from that.
Estimating the hyperparameters. Yes. So if you have a generative model and you fit the generative model, in this case, we are fitting as you say, we are estimating the hyperparameters as A and B in the baseball example, right? Then from there, yes, we can sample new data. Yes. And predict, I guess, future samples. Yeah.
Okay. Thanks. If we go back to the beta binomial model, right?
Yes.
At the denominator, we have a probability of P of D, right? So probability of observing data, right?
Well, sorry, let me bring it there first so other people can also see. Yeah.
Yeah, so on this slide, right, what do we mean by P of D? Because there's no given a particular N naught or N1, or there's no given a particular A.
Right. So actually, if you want to compute P of D, P of D. Oh, actually, we will actually discuss how to compute P of D in week 6. Actually.
Oh.
But here I guess. P of D is the probability of observing the coin tosses, right? While not knowing what is theta, right?
Yeah.
So actually, to do that, actually, if you want to compute P of D, right? So this is the beta binomial, right? So to compute P of D, this is equal to P, like this will be P of D and theta given d theta, right? And then this is equal to P of theta, P of D given theta d theta, right?
Yeah.
Right. And so then P of theta, we can plug in the beta distribution, right? And then this one we can plug in the likelihood, right? The binomial likelihood. And from here we can compute P of D. Actually, there is some overloading of the parameters. Actually, this will be a function of A and B, right? So actually, if I want to be a bit more explicit, I should have written P of D given A and B at the denominator, but I didn't do that. Yeah.
But if P of D doesn't depend on N0 and N1, then
no, P of D does depend on N0 and N1. Oh, sorry. It's a function of A, B, N0 and N1. Yeah, sorry. Okay. Yeah.
Right. Because the data we observe will have to depend on N0 and N1 as well.
Yes, of course. Okay. Yeah. I'm just saying that this distribution will change depending on the values of A and B. Yeah.
Right. Okay. Thanks.
Yes.
Uh, yeah, move. Actually, sorry. I have quite a few questions.
Since you paused, let's answer Huai's question first. So Huai's questions. Oh, slide 38. Oh, right. So as I was saying, I think you're referring to this point, right? So the idea is that once we have the joint distribution of X and Y, we can sample from this. And actually, we can then inspect our samples. If our sample looks realistic, then actually this means our generative model is good, right? I don't know if you all are familiar with, some of you are probably familiar with like the generative adversarial model, right? Generative adversarial network, right? So there, for example, people are able to use the network to generate highly realistic images, which suggests that actually their model is good, right? So the nice thing about generative model is that by sampling the data from the joint distribution that we learn, then it gives us a sense, we can get a sense of how well we're doing, and perhaps also give us a sense of how to improve our model. Does that answer your question, Huai? Yinchuan, you have other questions you were saying?
Yes. For our beta, like beta binomial thing, right?
Mm-hmm.
If we fit in A and B values which are less than 1,
Yes.
then a lot of the derivations, are they still valid? Because the mode is no longer correct.
Good point. Typically, I would set A and B to be great. Hold on, let me think. Right. Correct. So I think in all of this equation, this assumes A and B to be at least 1. Yes, you're right.
Okay.
Good point. Yeah, as you will see in the ungraded homework assignment, either today or is it this week or last week, I asked you all to show that there's quite a few special cases, right? Yeah.
Okay.
Yes. In lecture 1, the examples of P of X and Y is like the different size of white boxes. Sampling is like taking out these white boxes. No, actually. So for example, sampling would be, let me bring up the previous lecture. Sorry, 1 second. I'll just bring up the condensed version because let me share screen again. Oh, well, I was sharing screen. Confused. Okay. So here, right. So here, right. So sampling from this distribution means that you get a particular value of X and Y, right? So let's say this is like, for example, let's say this is 1, 2, 3, 4, 5, 6, 7. And then let's say this is Y is 1, 2, 3, 4, 5, 6, 7, right? So then sampling from this distribution, maybe the first time we sample, we might get 1, 1, right? The second time we sample, we might get 7, 1. The third time we sample, we might get 4, 4. Does that make sense, Samuel? Or who is Samuel asking? Does that make sense, Samuel? Yeah. Oh, okay. Yeah, that's what. Yeah. Okay, that's what I mean. Yep. Arunava, yes, the condition that says that A and B should be greater than, sorry, for the, let me bring the other slide. Okay, hold on, let me bring up the other slide. Hey, how do I do this? I need to exit first. And show. Okay, so let me switch back to the other slide. So, I need to also clear all the other stuff. Okay. So yes, so in this case, the beta distribution is defined for A greater than 0, B greater than 0. That's correct. What Yin Chun is asking is that does the sum of the formula still holds? For example, does this still holds if we set A and B to be less than 1? And the answer is that no. And the reason is that the mode. Actually, hold on. Yeah, are you sure the formula won't hold if A and B are less than 1? Like the mode. Oh yeah, they get very messy, right? Correct. Yeah. Yeah. Right.
Doesn't hold.
Right. I'm pretty sure that's not hold. Yes. So the problem is that in this derivation, I uses this mode, but this mode is not equal to, is not correct if A and B is less than 1, right? Because if A and B is less than 1, if you recall here, if A and B are less than 1, then it looks something like this, right? So then the mode will be like either 0 or 1. Okay, if A and B are less than 1, then the mode will be 0 or 1, right? And so that formula wouldn't quite work here. This formula here is not 0 or 1. Okay, and so this formula here that I show you only works if A and B are greater than 1. Okay. Yeah. Setting less than 1 doesn't really make sense since there are counts, right? Yeah, I guess. I mean, although I guess I don't know why. I mean, okay, maybe if I give you the coin and you believe that I'm kind of an evil person, I must have given you either a coin which is either biased to 0 or 1, then I guess you should assume that, yeah, you can assume that A and B are less than 1, I guess. Yeah. Maybe I'm very devious and I'm going to trick you with a coin where it's likely to be 0 or 1. Yeah. But you're right. I guess in practice, in practice, you would, yeah. In practice, I guess you can just set A and B to be at least 1. Yeah. How to choose the model distribution of parameters? I don't understand your question, Low Wei.
So excuse me, Professor, can you hear me?
Yes, I can hear you very well.
In these slides, it says that assume beta prior.
You're saying how do we know to assume beta prior?
Why it's beta prior?
Right, good point. Beta prior is chosen here because some statisticians has worked out that if we choose beta distribution, then we get a very nice property, which is that the posterior distribution is also beta. Yeah. You can also, of course, choose non-conjugate beta, non-conjugate priors as well. And it's just that the math will be harder to work out. Yeah. In fact, I think in one of the assignment, you will have one of the non-graded assignment. I don't know if it's this week or next week, you will have one of that. Yeah.
Okay, so there are many distributions we can choose, but here we choose beta prior as the distribution because it is a conjugate prior.
Yes.
Is that right?
Yes.
Okay.
You can also choose other distribution, and the math will be harder to work out, but you can. Yes.
Thank you.
Yep. For CA1 exercise 2.16 solution, how to come out? Huh? What? I'm confused.
I mean the ungraded assignment.
Oh, okay.
I can't understand the solution.
Okay, Ken, let me bring it up. I hope. Sorry, by the way, it's quite late. The people can leave if they want to. I'm happy to stay and answer questions, but people who leave can leave. Yeah. Sorry, you're asking about 2.16, right?
Yeah. Last question.
Oh, equation 12. Oh, okay. So what equation 12? Hold on. Oh, sorry. This do you mean the formula for the beta function? Is it the formula of the beta function is you just get from Wikipedia? Yeah. But actually, it's obtained because remember the beta function has to integrate to 1, right? So sorry, are you asking about the first equality or second equality? Oh wait, hold on. I should share screen, else people don't know what the hell I'm talking about. Okay, hold on. Are you referring to this equality, or you're referring to? Are you saying why this is true, or you're saying why this is true?
The right hand side.
Why this is true? Is it? Oh, this is true simply because remember b of a and b. If you integrate, we know this is true because the integral of this whole thing has to be equal to 1, right? Correct?
Okay.
So if we integrate this with respect to dx and it's equal to 1, this means that this integral with respect to dx must be equal to this, the denominator, right? Does that make sense? So that's why this is equal to this. Actually, what is harder to show is why is this equal to this? This one, I don't know. You will have to find some book. Someone has already shown it for us. Yeah. I think you have to use some it's not chain rule, integration by parts or something. Yeah, I think to show this. Yeah. Ulash is asking, SH, is it the pattern recognition book? Actually, good point. What the hell is SH? No, it's a Simon Prince book. Oh, did I say wrongly? Oops. Hold on. Sorry. Hold on. You mean, are you referring to SP? SP is a Simon Prince book, Ulash. Yeah, it's a Simon Prince book. Yeah. Let's go to Huaikai first. Why does Y in page 32 means output or parameter? You're talking about today's site, right? Huaikai. So you're asking Y means output or parameter. Here, Y is what your target variable you're trying to predict. Does that answer your question, Huaikai? And Daniel, this recording will be automatically uploaded to Luminous. Yeah. Yeah, so it's output. Yeah, I guess you can call it output. You can call it output, I guess. Yeah. And then Zhao Qi is asking the question about that, the baseball question. Oh, let me go there. Let's go to this. Not the baseball question, sorry. This question. So Zhao Qi is asking this question again. So in this question, oh, sorry. What? Sorry, 1 second. Here. Yeah, okay. So probability, now it's empty. Yeah, whatever. Okay. So probability John hits the next ball, right? is equal, given the history, correct, is equal to, we have to use this formula, correct? 20 plus 70 divided by 100 plus 70 plus 200, correct? So far, so good, right? So then probability, John. Oh, hold on.
Prof, I don't think we can.
Yeah, sorry, for the share. Flipping back and forth is confusing. Yeah. Probability John does not hit the ball, given the history, right? It's equal to 1. Let's call this A, right? So this is 1 minus A, right? Correct? So 1 minus A is, 1 minus 20 plus 70 over 100 plus 70 plus 200, right? So this is equal to the third answer, right? Which is 80 plus 200 divided by 100 plus 70 plus 200. Does that answer your question? Okay. Any more questions?
Prof, can I ask something about the MAP and ML?
Yes.
So, quite early in the lecture, you mentioned something about when n goes to infinity, MAP and ML estimates so-called converge to the same.
Yes.
How do we interpret this? And like, for example, in the photos and cats and chairs and humans example.
Oh no, but the photo cast, I already computed the posterior probability for you, right? So that's just something I made up. And sorry. So it's just something I made up. Like, because presumably as n goes to infinity, then these numbers would change, right? So this is for a particular, this is the results of a particular model, right?
Right.
So as n goes to infinity, these numbers will converge to something, right? And the 0.6 will change, 0.3 will change, 0.1 will change. And then eventually it'll converge to something which is the same as the ML estimate. Yeah.
So it's the so-called model parameters lah.
Right. Yeah. Well, I mean, do you consider the posterior distribution to be the model parameters? Like, I mean, is the MAP estimate? It's like the posterior distribution P of. So in the Dirichlet distribution example, remember that I was showing this, right? Right, as n goes to infinity, your distribution will become centered at the MAP estimate and the ML estimate, right? So it's kind of the same concept. As n goes to infinity, if let's say you're doing some estimation, the MAP estimate should converge to the ML estimate. In theory, yes. Yeah.
That's after you observe the coin toss or dice roll many times.
Yes. Yeah.
Okay.
The reason why I say in theory, because you can have your prior can say that 0.5 can never happen, right? Your prior can say that theta equal 0.5 is impossible, right? But actually the true value is 0.5, right? And so your ML estimate would converge to 0.5, but your MAP estimate will not converge to 0.5.
Oh, okay.
Because your prior says it's impossible, right? Correct?
I see. Okay, cool.
What does the second option represent? The second option in the baseball thing, it's just something I make up. Yeah. It's just something I make up. The baseball example, you mean the question? It's just a leer for people to select the wrong answer. This one, I don't know what this is. I don't know what is this one. Yeah, I just made it up. Yeah. It means nothing from what I can tell. Yeah, maybe it means something, but I don't know what it is. Yeah. So the top one is a probability that he will hit the next ball, and this one is a probability that he won't hit the next ball. I don't know what is this. Right. After 9 p.m., would it be recorded? I think it will still be recorded after 9 p.m. Yes. Yeah. I thought we could just replace 20 by 80 to get not hitting the next ball. You cannot do that. Yeah. You cannot do that.
Hi, Professor.
Yeah.
Hi, Professor. In the slide, let's model theta as a random variable. There's a graph, what is the y-axis represent? Is it the p of theta?
So which slide? Which slide?
The slide entitled "Let's model theta as a random variable."
Why don't you? What's the slide number? Maybe.
Approximately 18 or 19. 19. Sorry, it looks like.
Is this? Sorry, this is the beta binomial or what?
Yes. I mean I don't understand why this.
No. We should go to the slide first before you ask a question because I don't know what you're talking about.
Can you see my screen? I mean this picture.
Oh, hold on. What? Oh, right. Okay, I see. Okay. What about this? Yeah.
Yes. If the y-axis represents p of theta, then why the p of theta is larger than 1? I cannot stand that.
No. As I mentioned before, P in this case is the PDF. PDF can be greater than 1, right?
Oh, okay.
Yeah. In all of this, theta is continuous. Remember the piece of paper here. Here. Remember what I said, right? In this course, or in my part of the course, right? If I always use P of something. So if X is continuous, you can assume it's PDF. If X is discrete, you can assume it's PMF. Yeah.
Okay. Thank you, Professor.
Oh, no problem.
Hi, Professor.
Yes.
Can you hear me?
Yes.
Yeah, I have a question in slides 18.
Yes. Yeah.
I wonder why the theta and 1 minus theta's power is a minus 1, b minus 1.
Oh, sorry. I think we'll have a different slide. I'm using the non-condensed version, So, sorry, which part is this? The Dirichlet multinomial? Sorry, this is beta binomial or what?
No, actually, the title of the slide is "That model theta as a random variable."
Oh, so same as same.
Yeah, the same as the just one, the last
Okay,
one.
this one. Oh, okay, same as just one.
Right. I wonder the theta's power. Why is a minus 1, not a?
Oh. I mean, that's a very hard question. Just like asking me why is it Gaussian distribution is not x to the power 4, it's x squared. So someone has already worked it out, yeah. But I'm sure there's a reason for it, but I cannot tell you offhand what is it. Yes. Yeah.
Okay. Thank you.
I mean, you can always do a change on random variable, right? You can say A, you can always set A and B instead of A minus 1, but then of course, then you have to change it so that A and B can be greater than minus 1, right? You see what I'm saying?
All right.
But then
Okay.
I presumably that looks less clean, right? It's better to just say A minus 1, then you can say A can be greater than 0. Yeah.
Okay. Thank you.
Yeah. Oh, sorry. So, okay. So I guess, any more questions? Are we going to do some countdown again? And then someone's going to stop me at 5. Yeah, hey, Wai Kai.
Okay.
From the beta, sorry, Nitin is asking from the beta prior, can we say that A and B must be greater than 1? Well, I mean, okay, so the beta prior, A and B are greater than 0. However, for the formula I gave you here, the formula here assumes A and B are greater than or equal to 1. Does that answer your question? Okay. Oh, hold on. It's actually not that bad. Okay, sorry. Actually, it's actually not that bad because let's say A and B are 0, correct? Let's say if A and B are 0, right? As long as let's say, sorry, A and B has to be greater than 1, right? So let's say A is 0.1 and B is 0.1, right? It's actually still fine as long as we observe at least some coin toss, right? Then this distribution will still work fine, I think, right? Yanquan.
The MAP formula doesn't work if like you observe 5 heads and 0 tails.
Okay, that's possible. If it's all zeros, then yes, then it may not work. Yeah, then you will need to rework out this example. Yeah, this formula here. Yeah, I feel like this is a good exam question. No. I probably, well, actually, I don't know. I guess I reserve the right to ask this question. Yes. Yeah, I've not worked it out myself, but yeah. Okay. Blame me, Chen. You're gonna blame me. Yeah. Okay. Sorry. Any other question? But the deduce will change if A and B are smaller than 1. Actually, the formula may or may not change. It depends on N1 and N0 as well, right? So the thing is that this formula assumes that, wait, where's my annotation? This formula assumes that C and D are both greater than 0. Hold on. C and D are both greater than 1. Sorry. This assumes C and D are both greater than 1, right? If A and B are greater than or equal to 1, then we're done, right? Who cares? Right? Correct? Right? If A and B are less than 1, then it really depends on N0 and N1, right? If N0 and N1 are if N0 plus B or N1 plus A is somehow less than 1, then we cannot use this formula for the mode. Instead, we need to use the formula, then the mode will be either be 0 or 1. Then the MAP estimate will be 0 and 1. Does that make sense? Wiley? Yeah. Because this formula only holds when C and D are both greater than 1. If C or D are less than 1, then we have a weird situation, as you can see in one of the assignments, I think. Yeah. When less data, strategy 3 is better than half, 1 or 2. Why? When more data, are they the same? Yes. When more data, strategy 3, 2, and 1 will converge to the same result. When there's less data, obviously there's some luck involved, right? Strategy 3 can perform worse than 2 by luck. But in general, strategy 3 is better because it leveraged on the prior. Yeah. Strategy 3 leverage on the uncertainty that we have when we estimate from theta, right? Because if you look at this formula, right, notice that is taking into account the uncertainty in theta, right? Given that we've observed some coin tosses, we are not fully certain what is the value of theta, right? Correct? So strategy 3 takes into account our uncertainty about theta. So this is why strategy 3 is theoretically better. Okay, but of course you can always come up with some strange situation whereby, you know, it performs worse, right? Yeah. Does that answer your question, Xiao Yin? Can we assume n1 is not smaller than 1? And no, we cannot assume that. We cannot assume that. We cannot assume that. Yeah. Because let's say if you just toss the coin once, right? Then obviously either n1 or n2, sorry, either n0 n1 must be equal to 0, right? Correct? Zao Qi. So you cannot assume that. As in, no, you disagree, or oh, last slide. Oh, okay, I see. Last slide. Oh, you mean, sorry, what do you mean by last slide? You mean previous slide? We're talking about this again. Hold on. We're talking about this again. Is that what you're saying? No. Just to clarify, right? In Yan Chen's question, right? No matter what is the value of A and B, right? This formula is always true. This formula is always true, right? Correct. The MAP estimate is always the mode of this distribution. Okay, right? So this is always true as long as A and B are greater than 0. This is always true. And the MAP estimate is the mode of the posterior distribution, right? Correct? Now, what is tricky is that this formula here, right, assumes this formula for the mode, right? And this formula for the mode is only true if n1 plus A and n0 plus B is greater than 1, greater than or equal to 1. Okay, right? So if n1 plus A and n0 plus or n0 plus B is less than 1, then the formula, this formula, oh, I lost my mouse. Okay. Then this formula is no longer true and you have to use a different formula. Does that make sense, Zao Qi? Yeah, okay. Sorry, I was unclear. Okay. How? Any other people? Oh, there's more. I once assumed A equal 1B. I see. So did the driving instructor you picked, was it good?
Unfortunately, the guy didn't respond to my calls.
But it could be because he's very good, so he or she is too busy, too many clients. Okay. Okay, how are we all set? Should I do a countdown? Okay, so I'm gonna count down. Okay, we count down from 10. Any? Yeah. So 10. We'll end this once we count down to 0. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, all right. Have a good night, everyone. Bye-bye.